Somewhere above you, photons from Alpha Centauri are passing through Earth's atmosphere right now. They left their source 4 years and 3 months ago, crossed 40 trillion kilometers of open space, and arrived here carrying information about a star system they no longer represent. By the time any signal from Alpha Centauri reaches us, what it describes has already changed. We have no way to observe our nearest neighbor as it currently exists. Only as it was. For most of astronomy, that delay is so vast it barely registers as a distinction. At 4.24 light-years, it is close enough to feel like a solvable problem. It is not. In 1832, a Scottish astronomer named Thomas Henderson spent months at the Cape of Good Hope in South Africa, measuring the tiny angular shift of Alpha Centauri against the background of more distant stars as Earth moved around the Sun. He was cautious about his results, sat on them for 7 years, and finally published in 1839. The distance he calculated was roughly 4 light-years. In the nearly 2 centuries since that measurement, every refinement of the technique has converged on the same answer: 4.24 light-years to the nearest stellar system. The number has not changed. Our relationship to it has not changed either. Everything we know about Alpha Centauri, we know from light. Its surface temperature, inferred from the color of its spectrum. Its mass, calculated from the gravitational effect each star in the system exerts on the others over their nearly 80-year mutual orbit. The chemical elements burning in its atmosphere, read from the specific wavelengths those elements absorb as light passes through. The velocity at which it is moving toward us, measured from the compression of those same spectral lines. All of it, from light alone. Not a single physical sample. Not a single probe that has come within 1 trillion kilometers of the place. Nearly 2 centuries of accumulating knowledge, and every piece of it arrived at the speed of light, across 4.24 light-years of untraversed space. The question that the distance raises is not what we know, it is what light cannot carry. The total distance is roughly 40 trillion kilometers. To try to place that, the distance from Earth to the Moon is 384,000 kilometers. The distance from Earth to the Sun is about 150 million kilometers. Alpha Centauri is approximately 267,000 times that Earth-Sun distance. If you used the Earth-Sun gap as your unit of measurement and began counting, you would reach 267,000 before you arrived at the edge of the nearest neighboring system. There is a spacecraft currently traveling away from Earth called Voyager 1. It launched in 1977. It has been in motion for nearly 50 years, and it crossed into interstellar space, past the boundary where the Sun's solar wind gives way to the interstellar medium, roughly 12 years ago. It is now approximately 23 billion kilometers from Earth. Against the distance to Alpha Centauri, that represents 1/20% of the total journey. Nearly 50 years of continuous travel, 1/20% covered. Voyager 1 will not reach the vicinity of Alpha Centauri for roughly 73,000 years, and it is not heading in that direction. There is no spacecraft currently en route to our nearest stellar neighbor. Not one. The fastest spacecraft humanity has ever launched is New Horizons. At its peak, just after leaving Earth in 2006, it reached roughly 16 kilometers per second. At that speed, you could cross the continental United States in about 4 minutes. At that speed, the journey to Alpha Centauri would take approximately 78,000 years. 78,000 years, not 7,800, not 78. The asteroid that ended the Cretaceous period struck Earth roughly 66 million years ago. It wiped out approximately 3/4 of all species on the planet, including every non-avian dinosaur that had dominated terrestrial ecosystems for over 150 million years. 66 million years is a number that belongs to deep time, to geological strata, to extinction events, to the kind of duration that erases nearly all evidence of what came before. The journey to Alpha Centauri at the fastest speed any human object has ever reached would take approximately 1/846th of that interval, less than 1/10% of the time since the last mass extinction, not a geological duration at all by those standards. And still, no human civilization has existed for more than a small fraction of it. The entirety of recorded history, from the first cuneiform tablets pressed into clay in ancient Mesopotamia to this moment, spans approximately 5,000 years. A journey to our nearest stellar neighbor at that speed would require maintaining a civilization, with its accumulated knowledge, its technical capacity, and its memory of why the mission existed, for more than 15 times the entire duration of everything we have ever written down. The standard response to this is that future propulsion technology will close the gap. That systems not yet invented will reduce 78,000 years to decades. That is a reasonable hope, and it may eventually be a real one. It is also a hope that has remained perpetually in the future for as long as the problem has been clearly identified. Right now, in the present tense, 78,000 years is the number that the physics returns, and the physics does not negotiate. There is, however, one thing that has already reached Alpha Centauri, and has been reaching it continuously since the early 20th century. Radio waves from Earth's earliest broadcasts, traveling at the speed of light, would have arrived at the Alpha Centauri system beginning roughly 4 years after they were first transmitted. Every radio transmission, every radar pulse, every television broadcast emitted from Earth over the past 100+ years has expanded outward as a sphere of electromagnetic radiation. Whatever exists in the Alpha Centauri system has had a century of Earth's electromagnetic output pass through it. Faint to the point of near undetectability at that distance, but present. Light and radio travel for free. Physical mass does not. The word nearest in the phrase nearest star system is doing something strange that is worth naming. In ordinary use, nearest implies a category of objects at reachable scales. The nearest coffee shop, the nearest hospital, the nearest town. The word carries an implicit guarantee that nearness translates, however approximately, to accessibility. When astronomers called Alpha Centauri our nearest stellar neighbor in the late 19th century, they were making a purely relational statement. It is closer than any other star system. They were not making any claim about whether that closeness meant anything for travel or communication or contact. But language does not care about that distinction. The word nearest arrived in the public understanding carrying all its everyday implications, and those implications do not survive contact with the actual number. 4.24 light-years is nearest in the same sense that the bottom of the Mariana Trench is the nearest point on the ocean floor to the surface. Technically accurate, practically a different world. The space between stars is not a vacuum in the strictest sense. The interstellar medium, the gas and dust that fills the space between stellar systems, contains, on average, roughly 1 hydrogen atom per cubic centimeter. That is extraordinarily thin by any terrestrial standard. The best vacuum chambers built in physics laboratories contain more particles per cubic centimeter than the interstellar medium does. But it is not nothing, and its presence means that a spacecraft moving through it at any significant fraction of the speed of light would encounter increasing particle bombardment, a problem that scales with velocity in ways that current engineering cannot yet address. The interstellar medium is not the clean, empty corridor that intuition suggests. It is an environment that actively punishes high-speed transit in ways that only matter when the transit is fast enough to make the journey time reasonable. The faster you go, the harder the medium pushes back. None of this settles the deeper question. It sharpens it. If the distance is this real, and the nearest system is this remote in any practical sense, then everything we think we know about Alpha Centauri depends entirely on what we can learn from here without ever going there, and what we have managed to learn, and what we have gotten wrong. Across 4.24 light-years of separation is a story that starts with a planet that turned out not to exist. The name treats them as one thing. Alpha Centauri. Singular, a system, a neighborhood of 3 stars sharing a volume of space close enough to our own that astronomers have assigned them a common address. Alpha Centauri A, Alpha Centauri B. Proxima Centauri, sometimes called Alpha Centauri C. 3 names for what is implied to be a single family. But the distance between A and B on one hand and Proxima on the other is large enough that calling them a family is less a fact than an argument, and the argument is still being evaluated. Start with the 2 stars that are unambiguously together. Alpha Centauri A is a G-type star, the same broad classification as our Sun. It is slightly larger, with a diameter roughly 23% wider, and somewhat more luminous, putting out about 1.5 times the light our Sun produces over the same period. If you replaced our Sun with Alpha Centauri A and left every planet in its current orbit, Earth would be measurably warmer, but not dramatically so. It is, by the standards of stellar variety, our Sun's near twin. A little older, a little brighter, otherwise familiar. Alpha Centauri B is a K-type star, cooler, smaller, dimmer. Its diameter is roughly 14% narrower than the Sun. Its luminosity about half. K-type stars are sometimes called orange dwarfs, though the color difference from a G-type is barely perceptible to the naked eye at the distances involved. B produces less energy per unit time, has a somewhat calmer magnetic activity cycle than our Sun, and has been in that state for roughly 5 billion years. Both A and B are old enough that whatever instability marked their early lives has long since settled into something close to steady output. A and B orbit each other. Not distantly, the way Proxima does, but in a relationship close enough that their gravitational influence on each other is substantial and measurable. Their orbital period is just under 80 years. Which means that in the time between Henderson's measurement in 1832 and the present, they have completed fewer than 3 full orbits around their shared center of mass. The orbit is significantly elliptical, with an eccentricity of roughly 0.5, which means the distance between them is not constant. At their closest approach, they are separated by about 11 astronomical units, roughly the distance from our Sun to Saturn. At their widest, they pull apart to about 36 astronomical units, past where Neptune orbits our Sun. They spend a significant portion of each 80-year cycle relatively close together, then swing away and spend years at their maximum separation before drawing back in. At any given moment, the gravitational environment around each star is shaped by the proximity and mass of the other. When A and B are near their closest approach, the gravitational disturbance each exerts on the other's surrounding space is considerably larger than when they are at their farthest. Any planet attempting to maintain a stable orbit around either star has to do so against a background perturbation that changes over a cycle spanning longer than a human lifetime. The geometry is not static. It breathes on a timescale of decades. And then there is Proxima. Proxima Centauri sits roughly 13,000 astronomical units from A and B. To put that in terms of the system's own internal scale, A and B, at their farthest, are 36 astronomical units apart. Proxima is 13,000 units from both of them. If A and B were 2 lamps in the same room, Proxima would be another lamp located approximately 150 kilometers away. Same star-forming region, potentially. Same rough era of formation, but not in any ordinary sense of the word neighbors. Whether Proxima is a genuine member of the Alpha Centauri system, gravitationally bound on a long, closed orbit around A and B, or simply a star passing through the same region of space on its own trajectory, is a question that took decades to answer probabilistically, and has not yet been answered definitionally. In 2016, a careful analysis of Proxima's radial velocity and proper motion found that its path through space is consistent with a gravitationally bound orbit around A and B, with a statistical confidence high enough that most astronomers treat the binding as established. But consistent with and confirmed are different claims. The orbital period of Proxima around A and B, if it is indeed bound, would be somewhere in the range of 500,000 years or more. No human instrument has tracked a full period. No human civilization has existed long enough to observe even a small fraction of that orbit. What we have is a snapshot of 3 stars moving through space, and the snapshot is consistent with one being in orbit around the other 2. It is also consistent, at a lower probability, with a very slow hyperbolic trajectory that will eventually carry Proxima away entirely. The family may not be a family. It may be a stranger that has been walking beside us so slowly that we mistook its path for a permanent one. The system, whatever its membership, is old. The age estimate for Alpha Centauri A and B places them at approximately 5 billion years, which makes them somewhat older than our own solar system at 4.6 billion years. 400 million years of additional history. 400 million years during which, on Earth, no complex life existed yet, no fish had developed eyes, no land had been colonized by anything larger than microbial mats. Whatever has been happening in the Alpha Centauri system for those 400 extra million years, it has been happening without any observer here to note it. Age is not innocuous in stellar systems. A star's radiation output and magnetic activity change over time. In the early life of a stellar system, when the star is young and more active, it produces higher levels of ultraviolet and X-ray radiation, intense enough to shape or strip the atmosphere of any nearby planets. As the star ages and its activity decreases, the environment around it becomes different in character. Whether that change is good or bad for habitability depends on which planets exist, at what distance, with what atmospheric composition, and when in the star's life they formed. The relevant point is that Alpha Centauri A and B have had 400 million additional years of that process. Whatever it produced, it had more time to run. What strikes me about this is not the age itself, but what it implies about our position as observers. We are looking at a stellar system that has been operating for 5 billion years across 4.24 light-years of space, and we are assessing it from 2 pieces of evidence: light and statistical inference about trajectories. We cannot sample its planets, if it has planets. We cannot measure the composition of any atmosphere that might exist there. We cannot even confirm that the 3 stars sharing a name share a gravitational fate. The system is old, and we are new to watching it, and almost everything we call knowledge about it is, at a finer level of resolution, a well-supported estimate. There is one thing the system does not leave ambiguous. Its 3 stars are real, measurable, and have been observed in enough detail over enough decades that their basic properties are not seriously in dispute. We know what A is. We know what B is. We know Proxima exists, where it is, and how fast it is moving. What we do not know is whether what we call a system is a system, whether it has anything in orbit that resembles a planet, and if it does, what that planet is like. The second question has a history worth examining, because in 2012, astronomers announced that question had been answered. A planet orbiting Alpha Centauri B, Earth-sized, 4.24 light-years away, the nearest exoplanet ever found. And 3 years later, it was gone. Every planet in orbit around a star exerts a gravitational tug on that star. Not a large one. The mass difference is enormous, and the star barely moves in response. But barely is not zero. The planet pulls. The star shifts slightly in the direction of that pull, and then as the planet moves along its orbit, the star shifts back, and then shifts again in the opposite direction. The result is a tiny oscillation in the star's position, periodic, matching the orbital period of the planet. The oscillation cannot be observed directly at interstellar distances. The absolute movement is too small and the distances too large. But it leaves a signature in the star's light. As the star moves toward us, the wavelengths of its spectral lines compress slightly. As it moves away, they stretch. This shift is small but measurable, with a precise enough spectrograph. The technique is called radial velocity, and it has been one of the primary tools for finding planets outside our solar system since the 1990s. The challenge is calibrating what small means in practice. Jupiter, pulling on our own sun from 5 astronomical units away, induces a stellar wobble of about 12.5 meters per second, well within the reach of current instrumentation. Saturn, farther away and less massive, produces a wobble of about 2.7 meters per second, still detectable. Earth, the planet we are most interested in finding around other stars, produces a wobble in our sun of about 9 centimeters per second. 9 centimeters per second is the velocity of a slow crawl. Current instruments cannot reliably measure it. An Earth-mass planet orbiting Alpha Centauri B would produce a stellar wobble whose size depends on the orbital distance. A planet orbiting very close to the star, completing a full orbit in just a few days, would induce a somewhat larger signal than an Earth at Earth-like distances, because the closer orbit means a faster orbital velocity and a stronger gravitational pull per unit of time. The team that analyzed HARPS data in 2012 found a periodic signal in Alpha Centauri B's velocity at a period of 3.236 days, with an amplitude of approximately 0.51 meters per second. This was consistent with an Earth-mass planet at close orbital distance. It was also, at 0.51 meters per second, at the very lower boundary of what the spectrograph could claim to measure. The spectrograph in question is HARPS, the high-accuracy radial velocity planet searcher installed at the La Silla Observatory in Chile. It is among the most precise velocity measuring instruments ever built for this purpose, capable of detecting shifts as small as about 30 centimeters per second under ideal conditions. 0.5. 1 meters per second sits above that threshold in theory. In practice, the problem is not the instrument's sensitivity. The problem is everything else producing signals at the same scale. Alpha Centauri B is a living star. Its surface is in continuous motion, convective cells rising and falling, magnetic activity regions producing star spots that rotate in and out of view, oscillations propagating through the stellar interior, and expressing themselves as tiny periodic expansions and contractions at the photosphere. Each of these processes produces a signal in the radial velocity data. None of them are planetary. All of them are periodic. All of them have characteristic timescales, and none of them announce themselves as distinct from the planetary signal you are trying to extract. The stellar noise is not random. It is structured, periodic, and sits at amplitudes comparable to the signal you are looking for. Separating a real planet from this structured noise requires modeling the star's activity patterns, subtracting their contribution from the data, and examining what remains. The 2012 analysis did this. It found a residual signal at 3.236 days after accounting for stellar activity, and interpreted that residual as a planet. The 2015 reanalysis found something different. Not that the signal was wrong, it was there. But where it came from was not a planet. The signal arose from an interaction between two things: the structured noise of the star's activity and the specific schedule on which the observations had been taken. Radial velocity data is not collected continuously. Astronomers observe a target star on specific nights, at specific times, when conditions allow. The pattern of those observations, which nights, which gaps, how frequently, is called the window function, which has its own mathematical structure. When a periodic stellar noise signal interacts with a periodic observation schedule, The combination can produce an artifact signal at a frequency that is neither the stellar activity period nor the observational period alone, but a mixture of the two. The 3.236-day signal was such an artifact. It was real in the sense that it appeared consistently in the data. It was not real in the sense of corresponding to an object in space. The planet had been created, in a precise technical sense, by the rhythm of the telescope looking. The planet was not discovered and then disproven. It was proposed based on evidence that appeared persuasive at the time, but later proved insufficient to support the claim. That distinction is important because it changes what this episode tells us about our current ability to detect planets around Alpha Centauri. What it reveals is that an Earth-mass planet at close orbital distance around Alpha Centauri b, producing a radial velocity signal of roughly half a meter per second, sits at the threshold where stellar activity noise and data sampling artifacts become indistinguishable from the planet itself using current methods. Not that such a planet cannot exist. Not that it does not exist. That we cannot currently confirm whether it does. The sensitivity required to answer the question clearly is within the theoretical reach of instruments that either exist in early form or are under development. But as of the present, the question of whether Alpha Centauri b hosts an Earth-like planet in close orbit is exactly as open as it was before the 2012 announcement was made. The 3 years of apparent certainty were borrowed time. It is that the artifact and the real signal would have been almost identical in appearance. The window function artifact produced a periodic, coherent, statistically significant signature that passed the tests designed to distinguish real signals from noise. It did not fail any obvious check. It failed a more sophisticated one, applied later with more data. That means the question is not only whether Alpha Centauri has planets, it is also how we would know if the next detection were real rather than another interaction between stellar noise and the schedule of our watching. Radial velocity has limits at this scale. The obvious question that follows is whether a different method might succeed where radial velocity cannot. And the obvious candidate is the instrument that has redefined what we can see at almost every other scale of the universe, except, as it turns out, this one. Every optical instrument is designed for a specific range of brightness. Too dim, and the signal disappears into detector noise before it can be measured. Too bright, and the detector saturates. Not gradually, but suddenly, in the way that a camera pointed at the sun stops producing an image and starts producing a white field where all information has been lost. The engineering challenge in building any telescope is deciding where in the brightness spectrum the instrument will operate, because that decision shapes every other design choice that follows. The James Webb Space Telescope was built to operate at the faint end of that spectrum. Its primary mirror, 6.5 meters across and composed of 18 hexagonal gold-coated segments, collects light with an area roughly 6 times larger than its predecessor Hubble. Its instruments are cooled to temperatures near absolute zero to minimize the thermal noise that would otherwise drown out the faint infrared signals it is designed to detect. Its sunshield, a 5-layer structure about the size of a tennis court, blocks light and heat from the sun, earth, and moon to maintain the operating temperature of its detectors. The entire system was optimized, from its orbit to its materials to its cooling architecture, for one purpose: seeing things that are extremely, almost impossibly, dim. Alpha Centauri A has an apparent magnitude of about 0.01. Alpha Centauri B is about 1.33. Together, as they appear to the naked eye from Earth, their combined magnitude is roughly negative 0.27, making the system the third brightest point of light in the night sky after Sirius and Canopus. These are not dim objects. They are, in astronomical terms, blazingly, overwhelmingly bright. And that brightness is not a property that changes with instrument quality. It is a physical fact about how much energy per unit time per unit area is arriving at any detector pointed in that direction from Earth. JWST's detectors, built to register signals from galaxies whose light has been traveling for 13 billion years, would saturate when exposed to Alpha Centauri in timescales far shorter than a single readout cycle. The flux arriving from Alpha Centauri is not just above JWST's operational range by a small margin, it is orders of magnitude above it. Pointing the Webb telescope directly at Alpha Centauri with its primary scientific instruments would not produce an overexposed image. It would produce nothing useful, and might cause damage to the detector systems that would be expensive or impossible to repair at its current location, 1.5 million kilometers from Earth. The telescope has coronagraphs, devices that block the direct light from a star by factors of 10,000 to 100,000, allowing faint material in the surrounding region to be detected. These are used to study circumstellar debris disks, wide separation companions, and the environments close to bright stars without the starlight overwhelming the detector. JWST's coronagraphs can, in principle, be used to probe the region around Alpha Centauri at angular separations wide enough that the coronagraphic mask blocks the star's direct contribution. Some programs have investigated this possibility, but coronagraphy addresses only the most direct form of the problem. It allows observation of material well away from the star. It does not allow the characterization of close-in planets in the same way JWST characterizes planets elsewhere. The method JWST has used most powerfully to study exoplanet atmospheres is transit spectroscopy. When a planet passes in front of its host star as seen from Earth, a tiny fraction of the starlight filters through the planet's atmosphere before reaching the telescope. Different molecular species in the atmosphere absorb light at specific wavelengths, leaving signatures in the spectrum of that filtered starlight. By comparing the stellar spectrum during transit to the stellar spectrum outside transit, astronomers can identify molecules present in the planet's atmosphere: water, carbon dioxide, methane, and others. This is how JWST has studied the atmospheres of planets orbiting TRAPPIST-1. TRAPPIST-1 sits approximately 41 light-years away. That is roughly 10 times the distance to Alpha Centauri. Its planets are farther from us than Alpha Centauri's would be, and yet JWST can study them and cannot apply the same technique to any planet around Alpha Centauri because TRAPPIST-1 is an ultra-cool red dwarf star so dim that its apparent brightness in visible light is around magnitude 18, roughly 1 million times fainter than Alpha Centauri. JWST was designed for stars like TRAPPIST-1. It was not designed for stars like Alpha Centauri A and B. Transit spectroscopy also requires a confirmed transiting planet. Alpha Centauri has no confirmed planets of any kind, following the retraction of the 2012 candidate. Even if one were found by other methods, it would need to transit its star as seen from Earth's location, a geometric alignment that, for planets at habitable zone distances from Alpha Centauri A or B, would be very unlikely, and for the 3-day orbit candidate that was retracted, still uncertain. The method that has given JWST its most celebrated results in exoplanet science simply has no application to our nearest stellar neighbor in its current form. The situation produces an inversion that took me some time to hold clearly. Alpha Centauri is close enough that its stars are naked-eye objects, bright enough to navigate by, physically separated from us by a distance that is, in astronomical terms, negligible. If an Earth-sized planet orbits one of its stars, the planet is closer to us than any other exoplanet we know of by an enormous margin. By every intuition about proximity and observational advantage, Alpha Centauri should be the easiest system in the universe to study. Instead, the very properties that make it near, the fact that its stars are bright nearby sources rather than dim distant ones, are precisely the properties that put its planets beyond what our most powerful current observatory can characterize. The same energy that makes Alpha Centauri visible to the naked eye on a winter night is what renders it inaccessible to the infrared detectors that have begun describing the chemistry of worlds 40 light-years away. Nearness and brightness are the same physical fact at two different scales, and at the scale of JWST's instruments, brightness is not an advantage, it is a wall. This is not a temporary engineering limitation in the usual sense. Future instruments with better coronagraphs and higher contrast ratios may eventually be able to probe closer separations around nearby bright stars more effectively. Space missions specifically designed for direct imaging of nearby star systems, rather than adapted from instruments designed for different targets, would face a different set of constraints. But the specific instrument that exists now, the most powerful space telescope humanity has ever launched, is looking everywhere in the universe except the place that is most obviously next door. The reason has nothing to do with oversight or priority. It is a consequence of how sensitivity and brightness exist on opposite ends of the same spectrum, and of the choice made in designing JWST to push as far as possible toward one end of it. The telescope sees what it was built to see. What we cannot see from here with the tools we have is a question that has a specific answer at Alpha Centauri, and the answer points toward a different kind of problem, not the limit of what our instruments can detect, but the limit of what the physics of the place itself will allow us to confirm. A planet's orbit around a single star is, in the absence of other planets, essentially eternal. Left alone with one gravitating body, a small object traces an ellipse that does not decay, does not drift, does not require any ongoing process to maintain. The orbit is a solution to the equations of motion that perpetuates itself. The planet returns to the same point, at the same velocity, on the same schedule, indefinitely. Add a second star to that system, and the situation changes in a way that requires more careful thought. The planet is now in the gravitational field of two bodies simultaneously, one close and dominant, one farther away and weaker but never absent. The second star pulls on the planet with a force that changes in direction and magnitude as both the planet and the second star move along their respective orbits. The result is not a simple ellipse anymore. It is a path that is approximately elliptical, perturbed by the companion star's influence in ways that vary over the timescale of the binary's own orbital period. For Alpha Centauri A and B, that binary orbital period is just under 80 years, which means that any planet orbiting either A or B is subjected to a gravitational perturbation from the companion that cycles through its full range of directions and magnitudes approximately every 80 years. The strength of that perturbation depends on how close the two stars are at any given moment, and since their orbit is significantly elliptical, the perturbation is not constant. Near the close approach of about 11 astronomical units, it is roughly 10 times stronger than at the widest separation of about 36 astronomical units. The question planetary scientists ask about this situation is not whether the perturbation exists, but whether it is strong enough to destabilize potential planetary orbits, and the answer depends entirely on how far the planet sits from its host star. Close orbits are safer. A planet orbiting Alpha Centauri A at a distance of half an astronomical unit, for example, is dominated so thoroughly by A's gravitational field that B's perturbation, even at its strongest, is a small fractional correction. The planet processes around its small ellipse rapidly, completing full orbits in a few months, and the perturbation from B acts like a slow tide rather than a competing force. Stability under these conditions is robust and has been confirmed in numerical simulations. The boundary of that stability is not sharp, but simulations suggest that planets around Alpha Centauri A can maintain stable orbits out to roughly 2 to 3 astronomical units. Beyond that radius, B's influence becomes strong enough, at close approach, to nudge the planet's orbit in ways that compound over time, slowly stretching the eccentricity, then altering the inclination, eventually moving the planet's path into chaotic territory. The planet is not immediately ejected. The process takes millions of years, but the endpoint is the same: an orbit that no longer resembles the original, and a planet that is either thrown onto a very eccentric path or sent into the star. The habitable zone of Alpha Centauri A, the region where temperatures would permit liquid water on the surface of a rocky world, sits at roughly 1.2 to 1.4 astronomical units. That falls inside the theoretical stability boundary. A planet at Earth-like distance from Alpha Centauri A, completing its year in something close to 400 days, would have stable orbital mechanics in principle. The same is approximately true for Alpha Centauri B, whose lower luminosity places its habitable zone closer in, around 0.7 astronomical units, also within the stability zone around that star. The orbital mechanics of the adult system are not the main problem. The main problem is what came before, the era when planets were still forming. Planets do not arrive fully assembled. They build up over millions of years from the collisions of smaller bodies called planetesimals, objects ranging from pebble-sized grains to 100-kilometer rocks, gradually accumulating mass as they collide and merge. The process requires that most collisions be slow enough relative to the size of the objects involved that the impact is accretionary. Two objects hit each other and stick together rather than shattering apart. The orbital velocity of a planetesimal relative to its neighbors is the critical variable. Low relative velocities mean gentle collisions. High relative velocities mean violent ones. In a single star system like our own, the relative velocities of planetesimals in the inner disk are low enough during the planet-forming era that accretion proceeds reasonably efficiently, producing the rocky planets we observe on timescales of tens of millions of years. In a binary system, the companion star's gravity pumps the eccentricities of the planetesimals, continuously nudging their orbits toward higher elongation, which means higher relative velocities when they cross each other's paths. At some eccentricity level, the average collision velocity exceeds the threshold where the impact is more likely to erode both objects than to merge them. Rock shatters into smaller rock. Small rock is more easily blown away by stellar radiation. The reservoir of building material is depleted without producing a planet. Whether this effect was severe enough around Alpha Centauri B, in particular, to prevent rocky planet formation is a question the models have not resolved with consensus. Some simulations, using specific assumptions about the initial disk structure and the timing of various events in the binary's early history, find that terrestrial planets can form successfully despite the perturbations. Others find that the collision velocities become too high at critical stages of the accretion process, producing a system where the raw material never coalesces into full-sized worlds. The answer appears to depend sensitively on initial conditions that we cannot observe, because those conditions existed 5 billion years ago during a period that left no surviving record we can currently access. The stability argument and the formation argument are, in a sense, separate questions that both need to be true for a planet to exist. A planet could form, but then be destabilized over longer timescales, or the conditions for formation might never have been met. Or both requirements might be satisfied, and a planet might be waiting there now, inside a stable orbit, built from a disk that was disrupted but not destroyed. The three scenarios are observationally indistinguishable with current tools. The habitable zones around both Alpha Centauri A and B sit inside their respective stability zones. The theoretical windows overlap. The scenario of a rocky world at Earth-like distance from either star, maintaining a stable orbit, receiving comparable sunlight to Earth, is not ruled out by the physics of orbital mechanics. That scenario is, by the standards of what we know about planet formation, plausible. Plausible is not the same as likely, and likely is not the same as confirmed. But the category of physically impossible does not apply here, which is a narrower claim than it sounds. For many configurations in binary star systems, physical impossibility is exactly what the calculations return. Alpha Centauri's geometry clears that bar, and no higher one. The binary pair A and B orbits on its 80-year cycle, without any obligation to have produced planets, and without having yet told us whether it did. The third member of the system, separated from them by 13,000 astronomical units and by the uncertainty of its own gravitational membership, has told us something more concrete. Proxima Centauri has a planet. The news is less reassuring than it sounds. Proxima Centauri cannot be seen by the naked eye. At an apparent magnitude of about 11, it sits well below the threshold of what unaided human vision can detect under any sky conditions. To find it, you need a telescope pointed at a specific set of coordinates in the southern constellation Centaurus, in a region of sky that appears unremarkable through the eyepiece. It is the closest star to the Sun, and it is invisible to us without optical aid. The star that presents the greatest immediate relevance to the question of whether we are alone in the universe does not appear in any constellation, does not rise or set with observable brightness, and played no role in the navigation or mythology of any human civilization. The dimness is real. Proxima Centauri is a red dwarf, classified M5.5, which places it at the extreme cool end of the stellar sequence. Its mass is about 12% of the Sun's, its radius about 15%. Its luminosity in visible light is approximately 1/15 of 1% of what the Sun produces. A planet receiving light from Proxima at the same intensity Earth receives from our Sun would need to orbit at about 5/100ths of an astronomical unit, completing a full year in roughly 11 days. That is less than 1/5 of Mercury's distance from our Sun. The star is so faint that its warmth barely reaches. In visible light, Proxima is dim, cool, and quiet. In X-ray and extreme ultraviolet, it is something else entirely. Stellar magnetic activity is a product of the interaction between a star's rotation, its convective interior, and the dynamo processes that generate its magnetic field. In our Sun, that activity follows a well-documented 11-year cycle, rising to a maximum of sunspots and solar flares, and then declining, before rising again. The most powerful solar flare ever directly measured, the Carrington event of 1859, disrupted telegraph systems across Europe and North America and produced auroras visible at equatorial latitudes. That event had an estimated energy of roughly 10 to the 32 ergs, which is a number best understood by comparison rather than by itself. Proxima's superflares reach 10 to the 33 to 10 to the 34 ergs. That is 10 to 100 times the energy of the Carrington event, and unlike the Carrington event, which was an exceptional occurrence in a cycle that produces events of that magnitude perhaps once per century, major flares from Proxima occur far more frequently. Small flares happen multiple times per day. Significant flares energetic enough to matter for any nearby planet's atmosphere occur perhaps dozens of times per year. The most energetic events, the superflares, appear on timescales of months rather than centuries. The reason for this activity is partly structural. Red dwarf stars like Proxima are fully convective, meaning the entire stellar interior participates in the mixing of material from core to surface, unlike the Sun, which has a separate radiative zone below a convective outer layer. Fully convective stars generate magnetic fields differently, and the result, at Proxima's rotation rate and mass, is a star that is proportionally far more magnetically active relative to its total energy output than larger stars like our Sun. Proxima is dim and cold in its total energy budget, but its magnetic field produces violent, frequent discharge events that are enormous relative to what the star would otherwise be doing. The wavelengths that matter for planetary atmospheres are X-ray and extreme ultraviolet. These high-energy photons interact with atmospheric gases in ways that visible light does not. They dissociate molecular oxygen. They ionize atoms in the upper atmosphere, creating layers of charged particles that interact differently with the stellar wind, and critically, they attack ozone. Ozone is the product of photochemical reactions in a planet's upper atmosphere that provides the primary shield against the ultraviolet wavelengths that damage biological molecules. A planet that loses its ozone layer does not simply become a somewhat more irradiated version of itself. It becomes a planet where surface chemistry operates in a fundamentally different regime, one where the UV-sensitive bonds in amino acids and nucleic acids are continuously targeted by radiation that the atmosphere no longer filters out. Proxima b orbits at just under 0.05 of an astronomical unit, receiving a total radiation dose from Proxima that is estimated to be 40 to 100 times the equivalent radiation environment Earth experiences from the Sun across all wavelengths. During a superflare, the extreme ultraviolet flux at Proxima b's orbital distance can spike to thousands of times its quiescent level in a matter of seconds, then subside over minutes. The energy deposited in a single such event is enough to substantially alter the chemistry of an upper atmosphere lacking strong magnetic shielding. And Proxima produces these events regularly, on a planet that completes a full orbit every 11 days, meaning the rate of exposure per orbital period is very high compared to anything in our solar system's experience. The magnetic field question is unresolved in a way that matters. Planetary magnetic fields arise from the motion of electrically conducting fluid in a planet's interior, typically a metallic core undergoing convection. Earth's magnetic field, generated this way, deflects the solar wind and provides substantial protection against the direct impact of charged particles and some fraction of the high-energy radiation environment. Whether Proxima b has a comparable magnetic field is unknown, because we have no constraints on its interior composition. What we do know is that the planet is almost certainly tidally locked, one face perpetually toward Proxima and one face perpetually away, and that tidal locking affects interior dynamics in ways that may reduce or eliminate the convective activity needed to sustain a global magnetic field. This is not established. It is a plausible consequence of the orbital mechanics that has not been ruled out. The picture that emerges is a planet in the right zone for temperature but subjected to a radiation environment with no parallel in our solar system's current state. Habitable zone means the orbital distance where liquid water can exist on a planetary surface given the temperature the star provides. It does not include any assessment of particle radiation, UV flux, X-ray bombardment, or atmospheric retention. A planet can be in the habitable zone and simultaneously be the target of processes that make the surface incompatible with any chemistry we recognize as living. The term describes one variable in a problem that has many. Red dwarf stars like Proxima constitute roughly 70 to 75% of all stars in the Milky Way. They are, by number, the dominant stellar type in the galaxy. If the galaxy has a common kind of star, it is this one, and this most common stellar type produces, around its most common kind of habitable zone planet, a radiation environment that may be fundamentally incompatible with the kind of chemistry that produced the only life we know exists. That is not a conclusion. The question is genuinely open, and there are serious researchers on both sides. But it is a different kind of uncertainty than most. It is uncertainty about whether the most common address in the galaxy is livable at all. What we know about Proxima b itself is considerably less than what the headline suggested when it was confirmed. Its mass, its surface composition, its atmospheric state, and its interior structure are all outside current observational reach. What it receives from its star is not. When astronomers say a planet has been confirmed, they mean that independent observations using one or more methods have produced results consistent with the presence of an orbiting body, and that the probability of those results arising from noise or instrumental artifacts has been reduced below some threshold. The planet's existence as a gravitating object is considered established. What is not established, and what confirmation says nothing about, is what kind of object that gravitating body actually is. Its size, its density, its surface conditions, its atmospheric state, whether it is a rock or a compressed ball of water, or something with no analog in our solar system. None of that is contained in the word confirmed. The word names one layer of a problem that has many. Proxima b was detected in 2016 using radial velocity data from the HARPS and UVES spectrographs, and independently confirmed in 2020 with the Espresso instrument, which operates at higher precision. Each instrument measured periodic shifts in Proxima's spectral lines consistent with a body in an 11.2-day orbit at an orbital distance of roughly 5/100ths of an astronomical unit. The minimum mass of the orbiting body, derived from the amplitude of those spectral shifts, is approximately 1 Earth mass, perhaps slightly above. That minimum mass is not the actual mass. Radial velocity measures how fast the star is moving toward and away from us along our line of sight. If the planet's orbital plane is tilted relative to our line of sight, as is the case for the majority of orbiting planets, since most orbital orientations are not edge-on to any particular observer, then we are measuring only the component of the stellar wobble that points in our direction. The full wobble, corresponding to the full planetary mass, is larger by a factor that depends on the sign of the orbital inclination. If the inclination is 90 degrees, we see the full signal. If it is 45 degrees, we see about 70%. If it is close to face-on, we see very little, and the real mass could be far higher than the minimum we infer. For Proxima b, the orbital inclination is not known. No transit has been detected, which means the planet either does not cross the disk of Proxima as seen from Earth, or crosses it at a time and in a way that has not yet been caught. Without a transit detection, the inclination cannot be determined, and the actual mass remains bounded only from below. The minimum mass is approximately Earth mass. The actual mass could be twice that, 4 times that, or higher. Higher masses combined with a small planetary radius would suggest a dense rocky body. Higher masses combined with larger radii would suggest something more like a mini Neptune, a planet with a substantial gas envelope that makes it fundamentally different in character from Earth, despite being close in mass. We cannot currently distinguish between these scenarios. The radius of Proxima b is also unconstrained. Radius measurement requires a transit, during which the fraction of the star's light blocked by the planet passing in front of it encodes the ratio of the planet's cross-sectional area to the star's. Without a transit, we have no direct size measurement. The density of the planet, which would tell us whether it is primarily rocky, primarily icy, or has a thick, volatile envelope, cannot be calculated without both mass and radius. The planet's fundamental physical character remains unclassified by these basic metrics. The tidal locking inference deserves a separate assessment. At an orbital distance of 5/100ths of an astronomical unit, the gravitational differential across the planet's diameter from Proxima's pull is sufficient that the planet's rotation should have been slowed to match its orbital period over the course of millions of years. The timescale for this process is well within the age of the system. The expectation is strong enough that most models of Proxima b assume tidal locking as a starting condition, but it has not been directly observed. Tidal locking is an inference from orbital mechanics applied to an assumed planetary structure, not a measurement. If the planet is tidally locked, one face receives Proxima's radiation permanently, the other face never does. The temperature gradient between these two hemispheres would be extreme, potentially exceeding several hundred degrees across a single planetary surface. Whether an atmosphere, if one exists, can redistribute that heat through circulation is a question that depends on the atmospheric mass, composition, and surface pressure, none of which are known. Simulations have explored a wide range of scenarios. Some find that a sufficient atmosphere could maintain temperatures above freezing across a significant portion of the surface through atmospheric transport. Others find that the permanent night side would cause any water to freeze and the atmosphere to eventually collapse onto the cold face. The models are consistent within their assumptions. The assumptions span a wide range, reflecting how little the observations constrain. What the observations constrain tightly is a relatively short list. There is an object. It orbits with an 11.2-day period. Its minimum mass is approximately Earth mass. It orbits within the temperature-based habitable zone. Those four statements have high confidence. The geometry of the system and the behavior of Proxima itself are also well characterized. Everything else about the planet's nature is currently in a tier of inference, expectation, or outright unknowing that the word confirmed does not adequately signal. The distinction between these tiers is not a minor technical point. It determines what questions are answerable by more observation, which require fundamentally different methods, and which are currently beyond the capability of any instrument that exists or is currently planned. Whether Proxima b has an atmosphere is a question that could, in principle, be answered by a sufficiently sensitive next-generation telescope detecting spectroscopic signatures during a transit, if a transit occurs, and if the atmosphere has detectable features. Whether the surface, if a surface exists, harbors any form of chemistry that we would recognize as biological, is a question that could not be answered remotely by any instrumentation currently on the horizon. It sits in a different category of the problem. This is the particular shape of what we do not know about our nearest confirmed exoplanet. It is not a uniform darkness where all questions are equally unanswerable. It is a structured set of gaps, some of which are closer to resolution than others. The existence of the planet is established. The nature of the planet is not, and the gap between those two is where nearly all the interesting questions live. The most common way that gap gets crossed in public discussion is by moving from the confirmed minimum mass to statements about surface conditions from Earth mass to Earth-like, without acknowledging that the two terms describe different things and that the second does not follow from the first. An Earth mass object with no atmosphere, locked in place by the gravity of a flaring red dwarf at 1/11th of Mercury's distance from its star, would bear no resemblance to Earth in any way that matters for the questions people are actually asking. The mass is a property of the gravitational interaction. The habitability is a property of everything else. If the planet's surface cannot be directly characterized, can we at least determine whether the system holds any of the chemical signatures that would indicate biological processes operating somewhere within it? Detecting signs of life on another planet from a distance of 4 light-years requires solving several problems simultaneously, and the problems are not of equal difficulty. Some are engineering challenges, a matter of building larger mirrors, more sensitive detectors, better calibration pipelines. Others are more fundamental, rooted in the physics of what signals are available and what noise obscures them. The distinction matters because engineering challenges have solutions that money and time can provide. Physical constraints do not respond to funding or timelines in the same way. At Proxima b, the two types of problem are intertwined in ways that make the question of detection considerably harder than the distance alone would suggest. The main method for remotely detecting atmospheric chemistry on an exoplanet is transmission spectroscopy. When a planet transits its star, passing in front of the stellar disk as seen from Earth, so that starlight filters through the thin ring of atmosphere at the planet's edge before reaching our instruments. Different molecules in that atmosphere absorb light at specific wavelengths, leaving characteristic dips in the planet's transmission spectrum. Oxygen absorbs at certain infrared wavelengths. Ozone absorbs strongly in ultraviolet. Water vapor, methane, and carbon dioxide each have their own spectral fingerprints. A planet with photosynthetic life producing oxygen and an ozone layer would, in principle, leave a transmission spectrum distinguishable from a planet with no atmosphere or an atmosphere of nitrogen and argon. This method requires 3 things: a planet that transits, a star quiet enough that its own spectral variability does not overwhelm the atmospheric signal, and instruments sensitive enough to extract that signal from the combined starlight. For Proxima b, the status of each requirement is independently unfavorable. The transit probability for Proxima b is approximately 1.5%. That is not negligible. It means 1 in 67 systems like this one would produce a transit, but it also means that 66 in 67 do not. We have no detection of Proxima b transiting, and the geometry of its orbit relative to our line of sight remains unknown. If the planet does not transit, transmission spectroscopy is simply unavailable as a technique, not because of technology, but because of geometry. There is no amount of instrument sensitivity that can compensate for a planet whose orbital plane does not cross the stellar disk as seen from here. Assume, for the sake of working through the problem, that Proxima b does transit. The atmospheric signal we would be looking for, the wavelength-dependent variation in the transit depth caused by absorption in the planetary atmosphere, is small. For an Earth analog planet, this signal is on the order of 10 to a few tens of parts per million of the stellar flux. That is a genuine measurement challenge even around quiet stars. Around Proxima, the challenge is compounded by the stellar activity discussed earlier. Proxima's flares inject brief, intense bursts of ultraviolet and X-ray radiation into the stellar spectrum on timescales of minutes to hours. During a flare, the star's spectrum changes dramatically. The UV emission brightens by factors of hundreds. The overall spectral shape shifts. A planetary transit observed while a flare is occurring would produce a contaminated transmission spectrum in which the atmospheric signal from the planet is inseparable from the chromatic changes in the stellar emission itself. The flare has to be identified and removed from the data, a process that requires a precise model of what the flare is doing to the stellar spectrum at every wavelength simultaneously. That model is imperfect. The residuals of that imperfect removal become noise at exactly the wavelengths where atmospheric features would appear. Proxima flares frequently enough that observing a transit without some flare contamination is statistically difficult, particularly for a planet with an 11-day period, because long transits intersect flare events more often. Multiple transit observations would need to be averaged to build signal, with flare-affected observations excluded or corrected. The final data product, after all of this, would still contain systematic uncertainties from imperfect stellar modeling at levels that compete with the atmospheric signal being sought. Direct imaging with high-contrast coronagraphy can, in principle, spatially separate the light reflected by a planet from the light of its host star, then take a spectrum of that reflected light to look for atmospheric absorption features. The extremely large telescope, a 39-meter instrument currently under construction in Chile with a projected first light date in the late 2020s, will have coronagraphic capability intended in part for nearby stars. Proxima B's orbital distance of 0.05 of an astronomical unit corresponds to an angular separation of roughly 37 milliarcseconds at maximum elongation. That separation is at the inner edge of what the planned instruments can access. The contrast required to detect the planet's reflected light against the residual starlight after coronagraphic suppression is approximately 10 to the -7, 1/10 millionth of the star's brightness. Reaching that contrast at that angular separation is at the designed limit of the planned systems under ideal conditions. In practice, conditions are never ideal, and Proxima's variability would again contribute systematic noise to the residual stellar background that the coronagraph must suppress. The extremely large telescope may eventually achieve a detection or a spectrum of Proxima B's reflected light. It is also possible that the combined effect of angular separation, contrast requirements, and stellar variability will keep this target beyond reach even with that aperture. A further complication enters even if a spectrum is obtained. The interpretation of biosignatures around M-dwarf stars carries a specific ambiguity that does not affect Sun-like stars in the same way. Molecular oxygen can be produced abiotically, without any biological process, through the photolysis of water vapor by ultraviolet radiation. When water molecules in an upper atmosphere are split by UV photons, the hydrogen escapes to space, being too light to be retained, while the oxygen remains, accumulating over geological time. Proxima emits substantial UV during flares. A planet that once had oceans and lost its water to this process might accumulate oxygen in its atmosphere as a byproduct of atmospheric loss, not as evidence of photosynthesis. A detection of oxygen in Proxima B's atmosphere, if it were achieved, would therefore not be straightforwardly interpretable as a biosignature. It would require additional context. The simultaneous presence of molecular hydrogen or methane, which cannot coexist with oxygen at detectable levels over long timescales without ongoing production, would strengthen the biological interpretation. The absence of that context would leave the detection ambiguous between biological production and abiotic accumulation. Resolving that ambiguity would require more data, which would require more observations, which would require the original detection to have been possible in the first place. The layers of the problem do not collapse as each one is addressed. They tend to reveal the next one. The physical constraints around Proxima b are not uniquely severe relative to all other exoplanets. They are representative of the challenges that apply to the category of planets that, by every other metric, we most care about: rocky planets in habitable zones around nearby stars. The problems at Proxima b exist, in some form, at every target in this category. The nearest one shows them most clearly because it has been studied most carefully. The question of whether we can detect life at Proxima b from here, using light and the instruments attached to light-gathering mirrors, has a current answer that is honest without being hopeless. Not yet, possibly not for decades, and potentially not definitively even then. Whether other methods of investigation might succeed where spectroscopy fails is a separate question, and the oldest form of that question predates the discovery of Proxima b by several decades. In 1960, a radio astronomer named Frank Drake pointed an 85-foot telescope in Green Bank, West Virginia, toward two nearby stars and listened. The project was called Ozma, and it was the first systematic attempt in history to detect radio signals from another civilization. Drake chose Tau Ceti and Epsilon Eridani, both sun-like stars within 12 light-years, both accessible from the Northern Hemisphere Observatory. He listened for several months at a frequency near the emission line of neutral hydrogen at 1,420 megahertz, a frequency that Drake and colleagues had argued any technologically capable civilization might recognize as a natural channel for interstellar communication, the most common atom in the universe broadcasting at its most characteristic wavelength. The search produced nothing. A brief detection early in the program turned out to be aircraft radar. After that, quiet. Alpha Centauri, at declination -60 degrees, sits too far south to be accessible from Green Bank. The first searches for radio signals did not include the nearest stellar system, because the nearest stellar system cannot be seen by most Northern Hemisphere instruments. This is a geographic contingency with real scientific consequences. The history of SETI is partly a history of what could be observed from where instruments happen to exist. Southern Hemisphere searches, using facilities in Australia and South Africa, eventually extended the program to cover Alpha Centauri. The coverage became more comprehensive as the decades accumulated. The physics of what any radio search can detect is worth understanding before assessing what the silence means. Radio waves obey the inverse square law. Their power per unit area decreases with the square of the distance from the source. A transmitter broadcasting 1 kilowatt of power will deliver 1/4 as much power per square meter to a receiver twice as far away. At interstellar distances, this dilution is enormous. Earth currently radiates perhaps 50 to 100 megawatts in radio frequencies through leakage from television broadcasts, radar systems, and other sources. That is a significant amount of power by any terrestrial scale. At 4.24 light-years, that leakage would arrive at a receiver with an intensity well below what any current instrument could detect. A civilization passively monitoring our neighborhood would not be able to detect Earth's inadvertent radio emissions from Alpha Centauri's distance with any technology we know how to build. The flip side of that calculation is that we would not be able to detect equivalent leakage from Alpha Centauri either. If a civilization there is producing radio emissions at the level we produce, including broadcast television, civilian radar, and the ordinary electromagnetic noise of a technological society, those emissions are below the detection threshold of current and near-future radio telescopes across 4 light-years of space. The searches that have been conducted are not sensitive to the presence of a civilization roughly at our technological level going about its ordinary activities. What SETI searches can detect is deliberate, high-power, narrowband beacons. A signal produced by a large phased array transmitter, pointed specifically in our direction, carrying all of its power in a narrow frequency band to maximize the signal-to-noise ratio at the receiver, and that is detectable from Alpha Centauri with current instruments if the transmitter is powerful enough. The Arecibo message of 1974, transmitted once toward the globular cluster Messier 13, used a transmitter power of roughly 1 megawatt, but achieved an effective radiated power toward its target of about 20 terawatts through the directionality of the telescope beam. A comparable signal aimed at Earth from Alpha Centauri would be detectable. No such signal has been detected. Breakthrough Listen, the most comprehensive SETI program in history, launched in 2015 with substantial funding and access to multiple large radio observatories, including facilities in the Southern Hemisphere. It has conducted systematic surveys of nearby stars, including the Alpha Centauri system, at sensitivities and frequency coverages far exceeding earlier searches. The data collection and analysis have been ongoing, with results published in a series of papers. The current total of confirmed candidate signals of extraterrestrial technological origin from any target, including Alpha Centauri, is 0. Candidate signals are detected regularly, narrowband signals that initially resist explanation, and each one has been subsequently identified as radio frequency interference from human sources, satellite transmissions, or other terrestrial or solar system origins. None have survived scrutiny as potentially extraterrestrial. The silence is not uniform. It has structure. It covers certain frequency ranges and not others. It covers certain power levels and not lower ones. It covers signals that are narrowband and not broadband signals spread across many frequencies. It covers signals that persist when the telescope moves and not signals that disappear when pointing away from the source. Each of these limitations is real and quantifiable. The searches have been thorough within their parameters and have not extended beyond them. The parameters are themselves a consequence of assumptions about what a detectable signal from a technological civilization might look like. This is where the silence becomes harder to interpret than it first appears. We have been searching for radio signals because radio is what human technology produced in the mid-20th century when these searches were designed. The assumption that an extraterrestrial civilization capable of interstellar communication would choose radio frequencies has physical justification. Radio waves travel through the interstellar medium with low absorption, and the hydrogen line is a natural reference frequency. But physical justification is not the same as certainty. It is an argument about what seems reasonable given what we know, not a proof about what a civilization would actually do. A civilization that mastered interstellar communication might use radio. It might use optical lasers, which have been searched for but less thoroughly than radio. It might use modulated neutrino beams, which pass through matter without interaction, but require technology to produce that we cannot currently imagine. It might communicate through methods that do not have names in any human language because they involve physics we have not discovered. The range of possibilities is not infinite, being bounded by physical law, but it is considerably larger than what current searches have covered. The 60-plus years of radio silence from the direction of Alpha Centauri means, with high confidence, that no civilization there is intentionally broadcasting a high-power narrowband radio beacon toward Earth. It does not mean that no civilization exists there. It does not mean that no communication is occurring there. It means that one specific method of detection, applied for a human-scale duration in a universe billions of years old, has not returned a positive result. The silence is not nothing. It is a result. It tells us what is not happening at detectable power in the frequency ranges we have searched, toward the directions we have searched, during the time we have been searching. That is a genuine and non-trivial constraint. It is also a much smaller piece of the space of possible signals than the absence of any detection sometimes implies. The question underneath all of this is whether radio is the right frequency to be listening on. And that question has an answer that shifts the problem in a direction that the search programs did not anticipate when they began. The 1950s were the golden age of radio. The medium had matured from experimental technology into the dominant form of mass communication, and its physics were well understood. Radio waves traveled at the speed of light, passed through walls and atmosphere, could carry voice and music and information across continents with the right infrastructure. For anyone thinking in the 1950s about how two technologically capable civilizations might communicate across interstellar distances, radio was the obvious candidate. It was the most advanced long-range communication technology humans had ever built. That observation contains a problem that took time to articulate clearly. The assumption that other civilizations would communicate by radio is an assumption built from one civilization's position at one moment in its technological history. It is not derived from a general theory of optimal interstellar communication. It is derived from looking at what we had in the 1950s and asking what, scaled up, might work across light years. The search programs that followed were designed around an answer to that question, and the answer was radio because radio was what we knew. Consider the problem from a different angle. Human civilization has been producing radio emissions for roughly 130 years. That is a brief interval. If another civilization developed radio communication 10,000 years before us, their radio era is long behind them, as far behind their present as the Bronze Age is behind ours. Whatever method of long-range communication they use now was not invented 10,000 years ago by us, because we did not exist 10,000 years ago in our current technological form. The methods they might use now may not have names in any existing human language because we have not yet developed the physics to describe them or the engineering to build them. Searching for their radio signals is equivalent to listening for the sound of drums in order to detect the presence of a civilization that currently uses fiber optic networks. The drums may not have been used in 10,000 years. The alternative carriers that physics currently permits are illuminating precisely because of how difficult they are. Optical lasers are a genuine candidate. A sufficiently powerful, narrowband laser pulse aimed at a distant star system would be detectable by a receiver with a modest aperture. The directionality and energy per photon of optical light offer advantages over radio for certain communication scenarios. Optical SETI programs exist and have been operating for years, though with less coverage and funding than radio programs. No confirmed signal has been detected in the optical either, but the search space in optical frequencies is vast. The cadence of observations is irregular, and the technology for conducting comprehensive optical SETI surveys is less mature. The silence in optical is less characterized than the silence in radio. Neutrinos offer a different kind of possibility. Neutrinos interact so weakly with matter that they travel through the entire Earth with almost no attenuation. A neutrino beam could pass through a planet rather than having to go around it. Directed neutrino communication would allow signals to be sent through any line-of-sight obstruction that would block electromagnetic waves and would be nearly impossible to intercept accidentally. The cost of this property is production. Generating a usable neutrino beam for communication purposes would require particle accelerators operating at energies and scales that are not remotely within current human engineering capability. Detecting such a beam would require instrumentation of comparable scale. We cannot currently produce or detect directed interstellar neutrino communications. Whether a sufficiently advanced civilization could is not a question we can answer with our current understanding of particle physics. Gravitational waves, confirmed as a physical phenomenon by direct detection in 2015, carry energy through space-time at the speed of light and interact with matter only through tidal forces. A controlled gravitational wave signal would require the manipulation of masses at scales approaching stellar or black hole dimensions. The technology for modulating gravitational waves for communication is so far beyond current physics and engineering that it exists only as a theoretical possibility, not a practical one. But the point is not that these alternatives are currently achievable. The point is that the space of physically permitted communication channels is larger than radio, and our search covers one of them. The fact that we can imagine alternatives to radio does not mean that radio is necessarily the wrong choice. A civilization wanting to be found by civilizations at approximately our technological level might reasonably choose radio, because they would know that a technological species near the beginning of its communication era would have radio before it had anything else. If the goal of a beacon is to be received, broadcasting at frequencies and power levels accessible to the intended recipient is a reasonable strategy. The absence of such a beacon from Alpha Centauri is still informative, even if it does not answer the full question. No high-power, intentionally directed radio or optical beacon has been detected from the Alpha Centauri system in the decades of searching that have been conducted. That rules out one specific scenario: a civilization at Alpha Centauri actively broadcasting toward Earth with the intent to be received by an early radio-era civilization. Every other scenario remains open. A civilization there using different methods, a civilization there broadcasting but not toward us, a civilization there at a stage that predates or postdates our ability to detect them. The silence speaks clearly to one question. It does not speak to the others. What the silence most clearly reveals is the shape of our own uncertainty, not the shape of what is at Alpha Centauri. We designed a search based on our technology and found nothing that our technology was designed to find. The absence is about us as much as it is about them. It defines the limits of one kind of question we can ask. The other kinds of questions: what method might a civilization 10,000 years ahead use? Whether they would choose to broadcast toward us, whether their concept of communication maps onto anything we would recognize, those remain outside what any current search program can address. This is the situation as it stands after more than 60 years of active listening. A rich and well-characterized silence that tells us a great deal about one specific scenario and almost nothing about the broader question of what is happening in the nearest star system. Every conclusion from that silence requires appending a list of assumptions longer than the conclusion itself. The silence is real. Its interpretation is not settled. The question that follows from this is not about communication. It is about whether there is another path entirely, one that does not require a signal to be sent toward us and does not require us to have the right detector. The path of physically going there, or sending something that can. What that path actually looks like, and what it costs in physics rather than money, is a different kind of accounting. In 2016, a project was announced that represented the most serious engineering attempt in history to reach another star system within a human lifetime. Not a concept study, not a theoretical paper. A funded initiative with $100 million committed to the research and development phase, backed by physicists and engineers who had thought carefully about whether the physics allowed it. The project is called Breakthrough Starshot, and its central proposal is worth understanding in some detail, because the details reveal something important about the structure of the problem. The proposal works as follows. A ground-based laser array, drawing on the power of a dedicated facility, fires a coherent beam at a small spacecraft at the moment of launch. The spacecraft is not large. It consists of a light sail, a few meters across but nanometers thin, made of a reflective material capable of surviving intense laser irradiation. attached to a payload roughly the size of a postage stamp. A chip containing a camera, basic sensing instruments, a power supply, attitude control thrusters, and a laser for communicating data back to Earth. The total mass of each probe is on the order of 1 gram. The laser beam accelerates this gram-scale system to 20% of the speed of light over a period of minutes. At that speed, the distance to Alpha Centauri is traversed in approximately 20 to 22 years. The laser array required to achieve this is not small. The design envisions something on the order of 100 gigawatts of coherent laser output, focused through adaptive optics over a large aperture, maintained on a target for the duration of the acceleration phase. For comparison, the total electrical generating capacity of the United Kingdom is roughly 100 gigawatts. The Starshot laser array, in its full realization, would require dedicated power infrastructure of national grid scale concentrated into a single facility. The probes would be launched in quantity, many simultaneously or in sequence, partly because the attrition rate from technical failures and partly because more probes improve the odds of useful data return. The physics of this proposal, remarkably, checks out. There is no physical law that prohibits what Starshot describes. Laser acceleration of light sails is demonstrated at small scale. Miniaturized electronics of the required capability exist or are within sight of current development. The interstellar medium, while not empty, is sparse enough that a well-designed sail might survive passage through it at this speed, if the sail material is chosen correctly and the leading edge is hardened against grain impacts. The travel time of 20 years is within a single human lifetime. The proposal is not science fiction in the sense of requiring physics that does not exist. The problem is deceleration. At 20% of the speed of light, a gram-scale probe has kinetic energy roughly equivalent to the explosive yield of several tons of conventional explosive relative to any target it might encounter. It is not possible to slow this probe down at the destination using any mechanism carried on board. The mass of any braking system sufficient to reduce the probe's velocity would be far greater than the probe itself, defeating the purpose of the light sail approach. The star's radiation pressure could, in principle, provide some deceleration if the sail geometry were designed for it, but the calculations suggest that slowing from 20% light speed to a useful orbital or flyby speed using stellar radiation alone would take decades, and would require a sail area orders of magnitude larger than what could be accelerated by the ground array. What breakthrough Starshot actually produces, when examined carefully, is a flyby. The probe arrives at the Alpha Centauri system at 20% of the speed of light and does not stop. It passes through, makes observations, stores data, transmits what it can during and after the encounter, and then continues outward into deep space beyond the system. The window during which the probe is close enough to Alpha Centauri's planets to image them or measure their properties at useful resolution is on the order of hours. A few hours of proximity after 20 years of travel. During those hours, the chip's camera must image, its sensors must measure, its memory must store everything, and then the probe must transmit everything it has gathered back toward Earth using a laser the size of a fingernail. The link budget for that transmission across 4.24 light-years, with a transmitter of that size and power, is extraordinarily constrained. The amount of data that can be returned may be measured in kilobytes or megabytes rather than the gigabytes we take for granted from missions to the outer solar system. The Voyager spacecraft, still transmitting after nearly 50 years, uses a 23-watt transmitter and a 3.7-meter antenna to send data across the outer solar system. The Starshot chip must transmit across 4 light-years with a laser the size of a thumbnail. The data begins its journey back at the speed of light the moment it is transmitted. 4.24 years later, it arrives at Earth. Total time from launch to first data receipt, approximately 25 to 26 years. The interstellar medium poses a further challenge that the proposal is still working to solve. At 20% light speed, Hydrogen atoms in the interstellar medium are not obstacles to navigate around. They are projectiles, arriving at the probe's leading surface at 60,000 kilometers per second. The flux of particles at this relative velocity causes sputtering of the sail material, with atoms knocked off the surface layer by layer with each impact. Over 20 years of travel through even the sparse interstellar medium, the cumulative erosion could be significant. Dust grains, rare but not absent, pose catastrophic risk. A single grain of a few micrograms, impacting at 20% light speed, delivers the energy of a rifle bullet to a 1-gram target. The sail must somehow be designed to survive encounters that cannot be predicted or avoided. These are engineering problems, not physical impossibilities. They may be solved. The Starshot initiative exists precisely to work on them, and the funding is directed toward understanding each of these challenges in enough detail to determine whether they are surmountable and at what cost. The timeline for achieving a launch-ready system is measured in decades, not years. No probe from this initiative has been launched. No probe will be launched in the near term. What Breakthrough Starshot clarifies, even in its current theoretical form, is the difference between reaching a destination and visiting it. The probe would reach Alpha Centauri in the sense that it would enter the system's vicinity, gather what data it could in a brief encounter, and transmit that data home. It would not visit in any sense that implies presence, examination, or the ability to respond to what is found. It cannot be redirected. It cannot be instructed to look more carefully at something discovered in flight. It cannot orbit. It cannot land. It arrives, briefly, and then it is gone. What arrives, in other words, is not a visitor but a message. It is a set of instruments that passes through a place once and reports what it saw. The response to what it found, if any response were warranted, could not be acted on for at least another 20 years. The exploration loop, from launch to data to decision to next probe, spans longer than most scientific careers. The prospect of sending a message to Alpha Centauri and receiving a reply, whether from a probe or from something there, leads naturally to the arithmetic of that exchange. The numbers are not complicated, they are simply very large. A conversation requires certain things that we rarely have occasion to examine because they are almost always present. Two parties who are aware of each other at approximately the same moment. The ability of each to know what the other has just said before responding. A shared context that evolves together as the exchange proceeds. These conditions are so basic to the structure of dialogue that most languages build them into their grammar, their tenses, their pronouns. They are also conditions that cannot be met at 4.24 light-years. Not imperfectly, not slowly. They cannot be met at all, in principle, regardless of how powerful the transmitters or sensitive the receivers. Any signal sent from Earth to the Alpha Centauri system travels at the speed of light and arrives 4.24 years after transmission. Not approximately. Exactly that, because the speed of light in a vacuum is fixed, and the distance is what it is. A reply, if one were sent immediately upon receipt, would arrive at Earth 4.24 years after that. The minimum round-trip time for any exchange is 8.48 years. That number is not a technological limitation. It is a consequence of the geometry of space-time and the measured speed of light. No engineering advance can reduce it. 8.5 years. In 8.5 years, children born at the moment you sent a message would be starting secondary school when the earliest possible reply arrived. Political administrations would have changed. Research programs funded at the time of transmission would have concluded and published. The people most closely involved in composing the message would be nearly a decade older, and this is the fastest possible case, assuming the reply was sent at the moment of reception with no processing time whatsoever. The implications for any practical communication are worth tracing carefully. Suppose a probe, years from now, reaches the Alpha Centauri system and detects something unexpected, an anomalous signal, an unusual atmospheric signature, something that prompts the question, Should we look more carefully at this? The probe cannot be instructed in response. The instruction would take 4.24 years to arrive, by which time the probe, traveling at any significant fraction of light speed, would be far beyond the system. The probe must carry its entire decision logic with it before departure. It cannot ask questions. It can only implement what it was told before it left. For a crewed mission, the implications are more acute. Any medical emergency, any technical failure, any unexpected discovery that requires consultation with Earth would occur in an environment where the fastest possible response from Earth arrives 4 years later. Mission control in any practical sense cannot exist for a crewed Alpha Centauri mission. The crew would be more thoroughly autonomous than any human beings who have ever existed in recorded history, more isolated from any external authority or assistance than any ship's crew in the age of sail, more cut off from any real-time advice than any explorer who has ever lived. The concept that breaks most clearly under 8.5 years is not communication itself, but responsiveness. Messages can still be sent and received. Information can still travel. What cannot happen is adjustment, the back-and-forth refinement by which two parties calibrate their understanding of each other in real time. A question sent to Alpha Centauri cannot receive a clarifying follow-up before the answer arrives. An answer cannot know what has changed in the situation of the questioner between the time the question was sent and the time the answer was composed. Every exchange is between the sender as they were years ago and the recipient as they are now. It is a conversation between the past and the present, with no way to bridge them. This restructures what contact could mean if there were a civilization at Alpha Centauri. It would not be a dialogue in any sense human relationships use that word. It would be an exchange of monologues, each composed with full knowledge that the other party will be different when the message arrives, that the context of the original question may have changed entirely, and that any reply will itself be received in a context that neither party can fully anticipate. The first successful contact with an intelligence at Alpha Centauri would not be a conversation. It would be two civilizations sending long, careful documents to each other across a gap that makes improvisation impossible. There is a precedent for communication that works this way, though at much smaller delays. Diplomatic correspondence between distant states before reliable fast transport, when messages took months to travel by ship, requiring each letter to be composed with complete arguments and full context, because there would be no opportunity to clarify before the reply arrived. Scientific journals, which carry extended arguments without assuming the readers can ask questions of the authors in real time. These forms of communication evolved precisely because they could function without simultaneity. They carry information efficiently. What they cannot do is respond to what the other party is thinking right now, because there is no access to right now. 8.5 years renders right now meaningless as a shared concept between Earth and Alpha Centauri. Whatever is happening at Alpha Centauri at this moment, whatever state its stars are in, whatever its planets are doing, will not be known here for 4 years. Whatever is happening on Earth at this moment is equally invisible to anything at Alpha Centauri. The two places exist in each other's past, not each other's present. The universe does not provide a mechanism for them to share the present. The context drift over 8.5 years is not a minor complication. It is the central feature of the exchange. A message composed in response to a specific situation arrives at a destination where that situation has long since evolved, resolved, or been superseded. A reply composed in light of the original message arrives at Earth in a context that the reply's author could not have known. The two parties are always out of phase, always speaking to a version of the other that no longer exists. Scientific questions change in character over 8 years. Research programs conclude, fields shift, the questions that seemed most urgent get answered or get abandoned and new ones take their place. A question about the composition of an atmosphere sent in 1 decade might arrive at its destination in an era where that question has been partly answered by other means, rendering the reply redundant or irrelevant. The exchange does not build on itself the way a conversation does. Each round trip is between two moments separated by nearly a decade, with no way to acknowledge or incorporate what changed between them. The people who would compose a message to an intelligence at Alpha Centauri would not be the people who received the reply. A decade changes careers, changes the institutional landscape of science, changes which questions the culture considers urgent. The reply would arrive in an organization that might be structured differently, staffed by different people, and oriented toward different priorities than the one that sent the original message. The continuity required to receive a reply meaningfully, to understand its context, to compose a response that acknowledges what was said, requires an institutional memory that spans a decade as a minimum. Human institutions manage this, imperfectly. Libraries maintain it. Scientific disciplines maintain it over longer periods, but it is not automatic, and the 8.5-year minimum is just the lower bound. A full, multi-round exchange would span generations. The specific number, 8.5 years, belongs to the current moment. Alpha Centauri is not at a fixed distance. It is moving through space, and that motion has a component directed toward our solar system. The delay is not a permanent fact about these two systems. It is a fact about where they happen to be in their paths through the galaxy right now, and for the next several tens of thousands of years. That motion, and what it means for the character of the window we currently occupy, is a piece of the picture that rarely gets discussed. The stars do not stay where they are. Because the timescale on which stellar positions change significantly is long enough that the night sky appears fixed across any single human lifetime or even across recorded history. Constellations look the same now as they did in ancient Mesopotamia because the stars composing them have not moved enough in 5,000 years to produce a visible shift. But they are moving, all of them, each on its own trajectory through the galaxy, governed by its own velocity and by the large-scale gravitational structure of the Milky Way, the sky that astronomers in the far future will observe, tens of thousands of years from now, will have a different geometry than the one visible tonight. Alpha Centauri is moving relative to our solar system at a velocity that has both a component across the sky, called proper motion, measurable as a shift in its angular position over decades, and a component toward or away from us, measurable from the Doppler shift of its spectral lines. Alpha Centauri's proper motion is among the largest of any bright star. It shifts its position against the background of more distant stars by nearly 4 arcseconds per year in one direction and somewhat less in the other. Over a century, this amounts to a shift of several arc-minutes, detectable in comparing old photographs to new ones. Over a millennium, it is unmistakable. Over 10,000 years, Alpha Centauri will have moved through a considerable arc of the southern sky. The radial velocity component, the speed at which Alpha Centauri is approaching or receding along our line of sight, is approximately 22 kilometers per second, directed toward our solar system. That is not fast in human terms. It is roughly the cruising speed of a spacecraft making efficient use of a planetary gravity assist. But over astronomical timescales, it accumulates. In approximately 28,000 years, Alpha Centauri will reach its closest approach to our solar system. The distance at that point will be roughly 3.1 light-years, down from the current 4.24. That is not a dramatic reduction in proportional terms, but it represents a real change in the fundamental parameter of the problem. The one-way communication time would fall from 4.24 years to about 3.1 years. The round-trip minimum drops from 8.5 years to just over 6. The travel time at New Horizons speed would decrease from 78,000 years to something closer to 57,000 years. The numbers are better. They are still numbers that define the problem as firmly as the current ones do. After that closest approach, Alpha Centauri begins moving away. Slowly at first, then at an increasing rate as its trajectory carries it past the local region. In roughly 1,000,000 years, Alpha Centauri will no longer be the nearest star system to our own. Another star will have moved into that position. The title of nearest stellar neighbor belongs to Alpha Centauri for a cosmically brief period. We happen to be living in the middle of that period, closer to the midpoint than to either end. The window during which Alpha Centauri is nearest is measured in tens of thousands of years, a time span that dwarfs all of recorded history but is negligibly short on galactic timescales. Within that window, we exist now, after roughly 5,000 years of organized civilization and roughly 130 years of the technology needed to even recognize that Alpha Centauri is a candidate for investigation rather than simply a point of light. We have been technologically capable of thinking about Alpha Centauri seriously for about 1/300th of the remaining window, during which it will be the nearest neighbor. Whether that matters depends on what mattering means in this context. It is not a sign, a coincidence with meaning, or an invitation. It is simply a description of where two moving objects happen to be in their respective trajectories at the moment. A third thing, human civilization, became capable of knowing the distance between them. The geometry was not arranged with any observer in mind. It is the geometry, and we are in it. What the trajectory does clarify is that the window is finite and currently open. Whatever we will ever learn about Alpha Centauri at its nearest, we will learn in the next tens of thousands of years, not later. After the closest approach, the distance begins to grow again, and the problems of detection, communication, and travel get incrementally harder, not easier. The opportunity is not unlimited, and it is not defined by human political timescales or funding cycles. It is defined by orbital mechanics that care nothing about either. If there is a civilization at Alpha Centauri, it is also approaching us. The same motion that brings the star closer brings any planets around it closer, and brings any technology on those planets closer in the same proportion. Whatever separation exists now will be smaller in 28,000 years. Whatever communication would be possible at 4.24 light-years becomes marginally more possible at 3.1. The window is shared. Both endpoints of any potential exchange are inside it simultaneously, if they exist at all. This does not change the difficulty of the problem in any practical sense. The techniques that fail now at 4.24 light-years would not suddenly succeed at 3.1. The improvement is real but not transformative. A biosignature that cannot be detected from here now cannot be detected from here in 28,000 years either, unless the instrumentation has changed in ways we cannot currently foresee. The window's finiteness is a fact about the long arc of the geometry. The problems within the window are determined by physics, not by position. What the proper motion of Alpha Centauri introduces is a timescale for the problem that is distinct from the ones examined so far. The travel time, the communication delay, the observational challenges, these define what is possible at any given moment. The trajectory defines how long the moment lasts in astronomical terms. The moment lasts tens of thousands of years. Measured against the duration of civilizations we know anything about, that is a long time. Measured against the duration of the star's motion through the galaxy, it is brief. The question of whether human civilization will persist long enough to make meaningful use of the window is not a question astronomy can answer. It is a question about the kind of thing civilization is and what it tends to do over the timescales the window provides. That question connects to something larger about what it means for intelligence to exist in a galaxy structured the way this one is, and whether the typical trajectory of a civilization arrives at the tools needed to use such a window before the window is no longer at its widest. The oldest continuously operating institution in the world, depending on how you define continuously and institution, is probably somewhere between 500 and 1,500 years old. The University of Bologna, founded in 1088, is a common candidate, Some religious institutions make claims to older continuous operation, though the meaning of continuous becomes strained across schisms and reorganizations. A handful of Japanese businesses trace their corporate lineage across more than 1,000 years. These are extraordinary achievements of institutional persistence. They required generation after generation of people choosing to maintain the thing their predecessors had built, finding resources to fund it, adapting its structure to survive political upheaval, economic collapse, war, plague, and the ordinary entropy that dissolves most human organizations within decades. The effort to keep them alive across 1,000 years is staggering in retrospect. A mission to Alpha Centauri at the fastest speed any human object has ever traveled would require 78,000 years. That is between 52 and 156 times the age of our most durable institutions, depending on which institution you count. It is not a matter of building a better institution. There is no organizational design principle that has ever been demonstrated to work at that timescale, and no reason to believe one exists. The difficulty is not lack of imagination. It is the absence of any historical analog that would let us model what it would take. Consider what would be required. A mission launched today would need to be monitored, supported, and awaited by an unbroken chain of human institutions for 78,000 years. The people who launched it would need to have established something that their grandchildren and their grandchildren's grandchildren, through more than 3,000 generations, would continue to maintain. Not because of any immediate benefit, the mission would not return data for 78,000 years, plus the communication delay, but because the mission was sent. 3,000 generations is roughly the number of generations separating us from the moment Homo sapiens first left Africa. Over that span, every language currently spoken by a human being has evolved, diverged, and in most cases gone extinct. Every social structure, every economic system, every form of governance that currently exists came into being and will likely cease to exist. The species itself may be biologically different in ways we cannot predict. Whether the entity that would receive the data from a mission launched today would be recognizable as us in any meaningful sense, and that question does not have a reassuring answer. This is not pessimism about human capability. It is an observation about what 78,000 years does to everything, based on everything we know about what the last 78,000 years did to everything. The problem is not that humans are fragile. The problem is that 78,000 years is simply a timescale on which no organizational continuity has ever been demonstrated, and no physical law prevents civilizations from changing beyond recognition over such periods. Breakthrough Starshot, if it succeeds, changes this arithmetic significantly. 20 to 25 years from launch to data receipt is a timescale entirely within human institutional capacity. A project begun today with serious funding and human commitment could plausibly be completed, and its results received within the careers of people currently in graduate school. But Starshot requires solving engineering problems that have not yet been solved, at costs that have not yet been estimated fully, using political and institutional support that has not yet been assembled. Each of those requirements is also a continuity problem, just on a shorter timescale. The question of whether the project could maintain funding and focus through the political cycles, economic disruptions, and shifting scientific priorities of the next 25 years is not trivial. Human institutions regularly abandon long-term projects when immediate pressures shift. 25 years is manageable. It is also long enough to cross multiple election cycles, economic recessions, and changes in institutional leadership that could each individually derail a program. The ratio of required duration to demonstrated institutional durability at any given speed forms a constant feature of the problem. At current speed, the ratio is catastrophically large. At Starshot speed, it is within human range but still requires sustained effort across a quarter century. Any speed in between produces ratios in between, all of which are harder than they look from outside the institutions that would have to sustain them. The same physics that produces a 78,000-year travel time at New Horizons speed applies to any civilization at any stellar neighbor within this region of the galaxy. The problem is not specific to human capability. It is a structural feature of the distances between stars and the speeds at which matter can be accelerated with finite energy. A civilization 10 times more technologically advanced than ours, if 10 times more advanced, means achieving 10 times the specific impulse of any current propulsion concept, would reduce the travel time by a factor of 10 to roughly 8,000 years. Still longer than any organization in human history has sustained a continuous project. Still longer than every civilization we know about has existed. The number that changes this dramatically is not travel speed, but the ratio between the achievable fraction of light speed and the distance to the nearest neighbor. To make Alpha Centauri reachable within a single institutional lifetime, say 100 years, requires traveling at roughly 4% of the speed of light. To make it reachable within a single human lifetime requires roughly 20%, which is the starshot proposal. Each step toward those percentages requires energy inputs that scale enormously, and the engineering challenges compound at each stage. The gap between where we are and where we would need to be is not a gap in aspiration. It is a gap in the physics of propulsion and energy availability. The distance is at the near end of what interstellar distances look like in this galaxy, the nearest possible destination. And still, the gap between the timescale, the distance imposes, and the timescale over which civilizations demonstrably function is large enough that bridging it requires either physics we don't have or organizational continuity we have never achieved. That combination, minimum distance still outside institutional range, raises a question that is not about Alpha Centauri specifically, but about what the structure of the galaxy does to any civilization trying to reach beyond its home system. It is a question Enrico Fermi made famous by noting a simpler version of it in 1950. If interstellar travel is possible and intelligence is common, where is everybody? The phrasing that follows from the analysis here is slightly different. Not where is everybody, but why has nobody demonstrated that institutional continuity across interstellar timescales is achievable? The silence may not be about intelligence being rare. It may be about a structural problem that applies to all intelligence equally. 4 billion years ago, something in a warm, shallow body of water on the early Earth crossed a threshold that nothing before it had crossed. A cell with a membrane, a metabolism, and the ability to copy itself. The evidence of that first step is everywhere around us now, in every bacterium, every plant, every animal, every organism that has ever been classified as living. Life, once it began, proliferated. It found niches in hydrothermal vents and high-altitude ice and oxygen-poor sediment and the stomachs of animals. It adapted. It diversified. It persisted through mass extinctions and glaciations and asteroid impacts. It was, in the biological sense, astonishingly robust. It was also, for a very long time, extremely simple. For the first roughly 2 billion years of life on Earth, every living thing was a prokaryote. A cell without a nucleus, without membrane-bound organelles, without the internal architecture that makes complex multicellular life possible. 2 billion years. That is longer than the interval from the origin of multicellular life to the present day. Life in this simple form was not failing. It was thriving, diversifying, covering the planet, altering the atmosphere through photosynthesis in ways that would eventually make our own existence possible. But it was not becoming complex. The transition to eukaryotic cells, cells with a nucleus, with mitochondria, with the machinery that would eventually allow them to cooperate in multicellular structures, appears to have happened once. Not repeatedly, not in parallel, but in a single lineage at a single moment, roughly 1.5 to 2 billion years ago. Every animal, every plant, every fungus, Every complex organism alive today descends from that single event, the merger of an archaeal cell and a bacterial cell, one engulfing the other, producing an arrangement that neither would have been capable of alone. 2 billion years of simple life, and then this. Once, the pattern repeats. Sexual reproduction, the shuffling of genetic material between two individuals to produce offspring, appeared once in the eukaryotic lineage and became the dominant mode of reproduction for complex life. Complex multicellularity, with differentiated cell types performing different functions, appears to have evolved independently about 6 times across the history of life, but the specific architecture that allows the development of organs, nervous systems, and brains characterizes only one of those lineages. The Cambrian explosion, roughly 540 million years ago, saw the rapid diversification of complex body plans, including the first eyes, the first predators, and the first animals with hard skeletons capable of leaving clear fossil records. This happened once, in a window of geological time that was brief by the standards of what came before and after it. The nervous system emerged multiple times, but the specific organization that produces the kind of centralized neural processing associated with complex behavior and, ultimately, with cognition appears to be restricted to the vertebrate lineage. And within that lineage, the specific trajectory that produced language, symbolic thought, cumulative culture, and the ability to build telescopes and ask questions about neighboring star systems is, so far as we can determine, unique. Not unique in the sense of being special, unique in the sense of having happened once, in one lineage, on one planet. Each of these transitions is a candidate filter. Not a filter in the sense of something that kills, a step on the path from chemistry to civilization that requires specific conditions, specific timing, specific contingencies, and that the vast majority of planets with life never reach. A world that crosses the first threshold, producing self-replicating chemistry, might remain at the prokaryotic level for its entire geological lifetime. A world that produces eukaryotes might never produce multicellularity. A world that produces multicellularity might never produce nervous systems of sufficient complexity to generate the kind of behavioral flexibility that leads to technology. The evidence for this picture comes, paradoxically, from our own history. Each of these transitions is attested on Earth to have happened exactly once. Not once per continent, not once per ocean basin, not once per major extinction event. Once per biosphere, across 4 billion years. The transitions are not impossible. We are here as evidence that they are possible. But possible and probable are different claims. A transition that happens once in 4 billion years on a planet with abundant chemistry and energy and time is not a transition that we should expect to find on every planet that has simple life. This reframes what the silence at Alpha Centauri tells us, or might tell us, if we could hear it clearly enough. The question is not only, is there life at Alpha Centauri, but if there is life, where is it on this sequence of transitions? Simple prokaryotic life covering the surface of a planet is, in principle, detectable by biosignature spectroscopy under the right conditions. But simple life is not what the SETI programs are listening for. They are listening for the product of an entire chain of transitions, every one of which appears to have happened once on the one planet we know anything about, in a sequence spanning 4 billion years. The universe might be full of planets hosting something like bacteria. The quiet that SETI hears might not be the silence of empty planets. It might be the silence of planets that never crossed the eukaryote threshold, or that crossed it and never reached multicellularity, or that reached multicellularity and never developed centralized nervous systems, or that developed nervous systems and never found the specific architecture that leads from sensation to cognition to language to the sustained inquiry that produces radio telescopes. Each step filters the initial set further, and the filtered set is what produces detectable civilization. Where Alpha Centauri sits in this sequence, if it sits anywhere in it at all, is currently unknowable. We cannot detect prokaryotes at 4 light-years with any existing or planned instrument. We cannot detect eukaryotes. We cannot detect multicellular life. We can, in favorable circumstances that do not currently obtain, look for atmospheric signs of metabolic activity in a confirmed transiting planet with a stable star, which Proxima b probably does not have, and Alpha Centauri A and B do not have confirmed planets to offer. The filter that matters for what we can detect is not the great filter in the abstract. It is the filter between any life and life that has been on this planet long enough and developed far enough to produce atmospheric signatures or electromagnetic signals that cross 4 light-years and remain distinguishable from stellar noise. That filter is the whole of biological history. And the whole of biological history, on the only planet we have data from, consumed 4 billion years and produced its most technologically capable lineage exactly once. Right now, as you are listening to this, photons from Alpha Centauri are arriving at Earth. Right now, in the time it takes to exhale, thousands of photons from a star 4 light-years away are striking the upper atmosphere, scattering through it, reaching the surface, falling on whatever is outside. Rooftops, grass, water, the skin of anyone who happens to be outdoors. The same photons falling on every optical telescope pointed in the right direction in the southern sky. The same photons that have been making the journey continuously, in an unbroken stream, since before any human being was alive to receive them. These photons left Alpha Centauri 4 years and approximately 3 months ago. The current date is what it is, and 4.24 years subtracted from it places their departure in a specific month of a specific year that you could identify if you wanted to. The light reaching Earth from Alpha Centauri tonight was emitted by those stars when specific events were occurring on Earth that you might remember or have read about. It is not light from the distant past in the way that starlight from the Andromeda Galaxy is light from 2.5 million years ago. It is light from the recent past, from years ago, not millennia. The physicists who designed the instruments that first measured Alpha Centauri's distance did so by analyzing this light. Not by sending anything out and waiting for it to return, by reading what arrived. The spectrum of Alpha Centauri's light encodes the temperature of its photosphere, the pressure and chemical composition of its outer atmosphere, the velocity at which it moves toward or away from us, and the period of its magnetic activity cycle. All of this information has been crossing the gap between the two star systems for as long as there has been a gap to cross, billions of years of uninterrupted transmission, much of it arriving before there was anyone here to receive it. What the light does not carry is more difficult to hold on to, because it is not an absence that announces itself. The photons arriving tonight were emitted during a specific state of the Alpha Centauri system as it was 4 years ago. Any change that has occurred in the system since those photons departed is currently in transit. It has not arrived. If Proxima Centauri underwent a significant superflare this morning, its light has been traveling for approximately 16 hours at this moment, and will take another 4 years and roughly 3 months to arrive. Whatever state Proxima b's atmosphere is in right now, we will have access to no information about it for over 4 years. For a galaxy 2 billion light-years away, the light we receive was emitted before complex life existed on Earth. The gap between what we see and what is happening there is so large that the word now loses all practical meaning as a shared concept. Alpha Centauri is different. The delay is 4 years. 4 years is a human interval. It is long enough to produce genuine uncertainty about current states. It is short enough that you can identify specific things that happened on Earth during the same period and feel the proximity of it. The implication, held precisely, is that the Alpha Centauri we can observe is not the Alpha Centauri that exists. The one that exists is the one 4 years ahead of what we can see, the one whose current state is encoded in light that hasn't reached us yet, traveling toward us right now, and won't arrive until sometime in the late 2020s. What any telescope observing Alpha Centauri sees is a slightly historical version of the object. Not the object's distant past, not its deep history, but its recent past. A version of it that is separated from the present by the time it takes light to cross 4.24 light-years. There is a specific strangeness to this that increases the closer the source is, not the farther. For distant stars and galaxies, the time delay is so large that it becomes simply a fact about how old the information is, interesting scientifically but not experientially immediate. Alpha Centauri is close enough that the delay is personally legible. You can think back to what you were doing 4 years ago. The light falling on you tonight left Alpha Centauri when that was happening. The current state of Alpha Centauri left those stars sometime around now and will arrive when something else is happening that you don't know yet. The stream of light from Alpha Centauri is continuous and has been since the system formed. What arrives is always a message from the recent past. What is happening there in the present moment is always already being transmitted but hasn't been received. This is not a metaphor for anything. It is the literal physical situation. Information encoded in electromagnetic radiation traveling at a fixed speed across a fixed distance, with the consequence that what we can know about the system is always a few years behind what the system is doing. The gap is narrow enough to count in human terms. It is too wide to close. The light carries a great deal. Everything that can be expressed in the spectrum is there. Temperature, composition, velocity, activity cycles, the presence or absence of flares during the emission window. Future instruments will be able to read more from the same light than current ones can, extracting signals that are present but not yet retrievable with available technology. The light is, in a sense, ahead of our ability to fully decode it. More information is arriving than we know how to receive. What the light cannot carry is presence. Knowing the temperature and composition of Alpha Centauri B's photosphere does not constitute knowing the system the way you know a room you can enter. It is a different category of knowing, intimate in some ways and permanently external in others. The information arrives on its own, without any effort on our part, from a source that has been broadcasting continuously without any knowledge that we exist. We receive it the way you might receive light from a window across a courtyard at night, seeing what the light reveals about what is inside, without any access to the inside itself, and without any way to signal back that you are watching. The question that follows from this is not what the light tells us, but what it cannot tell us, regardless of how precisely we measure it. Some questions about Alpha Centauri are answerable in principle from here, with better instruments or better methods. Others are not answerable from here under any circumstances, because the answer requires being there, or at least having something there that can report back. The boundary between those two categories is where the epistemology of the problem lives, and it is more specific than it first appears. There is a question you could ask about Proxima b that has a definite answer. Not a probabilistic answer, not an estimate, not a range. A definite, specific answer that is true in the way that the temperature in a room is true. The question is, what does the surface of Proxima b look like right now? If Proxima b has a surface, if it is a rocky world rather than a gas or water-dominated one, that surface is doing something specific at this moment. It has a temperature distribution across its face. The side toward Proxima is receiving radiation. The side away from Proxima is not. There may be geological activity, tectonic movement, volcanic emissions, or none of these things. Whatever it looks like something. The answer exists. It is not a question that lacks an answer. It is a question whose answer is completely inaccessible to us by any physical means that does not violate the structure of space-time. This distinction matters and is easy to collapse. Most unknowns in science are unknowns because we haven't developed the right method, or haven't built a sensitive enough instrument, or haven't looked in the right direction. These are engineering unknowns, and they resolve with effort and resources. A different category of unknown exists, though it receives less explicit attention. Questions that are unanswerable, not because of insufficient technology, but because the answer requires information that the physics of the situation cannot deliver. These are structural unknowns. What the surface of Proxima b looks like right now is a structural unknown. No telescope, no matter how large, can answer it from Earth, because any light from Proxima b's surface that is reaching Earth right now left Proxima b 4.24 years ago. What we can observe is what the surface looked like then. What it looks like now is encoded in light that has not yet arrived and will not arrive for 4 more years. The distinction between engineering unknowns and structural unknowns produces a map of what is knowable about Alpha Centauri, and that map has a specific shape. Some questions about the system are engineering unknowns. Whether Alpha Centauri A has a planet in its habitable zone, for example, is in principle answerable by radial velocity observations sensitive enough to detect the planetary signal above stellar noise, or by direct imaging with sufficient contrast ratio. We do not currently have the tools to answer this question reliably, but no physics prevents the tools from existing. The answer is on the accessible side of the boundary. Some questions are at the engineering structural boundary. Whether Proxima b has an atmosphere is in principle addressable by transit spectroscopy during a confirmed transit, but Proxima b has not been confirmed to transit, and Proxima's activity makes spectroscopic extraction extremely difficult. This question sits near the boundary. Possible in principle if favorable geometry and instrument capability coincide, but not guaranteed to ever be resolved. The question is not structurally unanswerable, but it may remain unanswered not because physics forbids it, but because the required conditions are very unlikely to be met. Some questions are structural unknowns from here, answerable only by presence. The detailed composition of any rocky surface in the Alpha Centauri system falls here. The resolved topography of any planet. The presence of liquid water at a specific location. The distribution of any atmospheric chemistry at fine spatial resolution. These are answers that require being near the object. Not because our telescopes are too small, but because the photon flux from a planet-sized surface at 4 light-years across the area of any planet's face is far too small per unit area to reconstruct with any instrument operating from Earth. Even a telescope the size of Earth's orbit could not resolve the surface of a planet at Alpha Centauri with current understanding of physical limits. The light simply does not carry enough photons per square meter of detector to form an image. There is a further category that connects to what Act 16 established. Questions about the current state of anything at Alpha Centauri. Not the past state, not the state as of a few years ago, but the state at this moment. These questions are structurally unanswerable, not because of limited resolution, but because of the finite speed of information. Whatever is happening at Alpha Centauri now cannot be known here now. This is not a gap that closes with better technology. It is a consequence of special relativity, which prohibits the transmission of information faster than light. The right now, in any question about Alpha Centauri's current state, is physically inaccessible to any observer on Earth, permanently, regardless of any future development. Alpha Centauri is close enough that we can know a great deal about its stars from photometric and spectroscopic observations accumulated over decades. We know the mass, temperature, luminosity, age, composition, and magnetic activity cycles of each star to a precision that many farther stars cannot match. In terms of our knowledge of the stars themselves, proximity has been an advantage. But for questions about planets and surface conditions and current states, proximity works differently. The 4 light-year distance is close enough to feel navigable, close enough to make the delay concrete and human scale, close enough to make the engineering unknowns feel within reach. And yet it is far enough that the structural unknowns are genuine and permanent, and the gap between what we can know by remote observation and what we could know by physical presence is enormous. From here, with remote observation, we can know the stars well. We may eventually determine whether they host planets. We may, under favorable conditions, determine whether any planets have detectable atmospheric signals of certain kinds. We cannot know the surface conditions of any planet there. We cannot know the current state of anything there. We cannot know whether any process we are observing is still ongoing or ceased 4 years ago. And we cannot access any of the information that requires spatial resolution finer than what the photon count from planet-sized surfaces at 4 light-years allows. The boundary between knowable and unknowable from here is not arbitrary. It follows from the physics of electromagnetic radiation, the speed of light, and the distance. It is a map drawn by physics, not by current human capability. Some of what lies on the unknowable side will remain there regardless of what technology develops, because the constraint is not technological. It is structural. This is not a reason to stop looking. The knowable side contains genuine answers to genuine questions. And those answers have changed how we understand the system significantly over the past century, and continue to change. But holding clearly what is on each side of the boundary is different from assuming that everything is knowable with sufficient effort. Some things are not. At Alpha Centauri, specifically, the most interesting questions about surface conditions and the current state of any life that might exist there are, from here, on the unreachable side. The boundary is 4.24 light-years wide, and it is made of time. Stars form from gas clouds. The process is governed by physics, the balance between the inward pull of gravity and the outward pressure of gas and radiation, the angular momentum of the collapsing cloud, the local magnetic field, the temperature of the surrounding medium. These parameters determine how much mass concentrates into each stellar body before the resulting star ignites and begins blowing away the remaining gas, preventing further accretion. The process is not random. It has characteristic outputs. It produces stars at a density that reflects the conditions under which they formed, and that density is not something any subsequent civilization can alter. The average distance between neighboring star systems in our region of the Milky Way is approximately 4 to 5 light-years. This is not the distance to our nearest neighbor specifically. It is the statistical average derived from the observed density of stars in the galactic disk near the Sun. Any civilization that arises around any star in this region of the galaxy inherits this number. Their nearest neighbor is, on average, 4 to 5 light-years away. They did not choose this. They cannot change it. Moving a star requires energy on the order of the star's total lifetime output applied over the travel timescale, and there is no mechanism by which any civilization we can currently conceive of would accumulate and direct energy at that scale. The interstellar distance is fixed, for practical purposes, by the physics of how the galaxy formed. At the speeds currently achievable by any human spacecraft, the transit time to the nearest stellar neighbor is on the order of 70 to 80,000 years. At breakthrough starshot speeds, approximately 20% of light speed, transit time falls to roughly 20 years. In the 20-year travel case, the probe arrives and departs in hours without stopping. In the 70,000-year case, the institutional continuity problem renders the mission practically impossible. Neither case produces what would normally be described as exploration in any meaningful sense. An ongoing presence, the ability to return, the accumulation of knowledge through extended contact. Now take this arithmetic and apply it not to us specifically, but to any civilization in the galaxy. Whatever technology any civilization develops, they face the same underlying parameter. The distance to their nearest neighbor is approximately 4 to 5 light-years. The physics of their universe is identical to the physics of ours. The energy required to move at significant fractions of light speed scales with mass and velocity in the same way. The interstellar medium poses the same particle bombardment problem at relativistic velocities. The organizational continuity problem applies to any intelligence that has finite institutional lifespans. The structural constraint at 4 light-years is not specific to us or to this era. It is a structural constraint built into the galaxy. This means something specific about the universe as a place for civilizations to exist. Each civilization that arises has, at current and near-future levels of technology, a reachable radius that is essentially their home system, the planets, moons, and smaller bodies orbiting their own star. With extraordinary investment and across human-relevant timescales, that radius extends to perhaps a few dozen light-years using Starshot-class technology, but only in the form of flyby probes, not in the form of anything that can stop, observe, and return. The reachable portion of the galaxy for any given civilization is an infinitesimally small bubble compared to the 100,000 light-years of the galactic disk. What this galaxy-wide structural constraint produces is a specific pattern. Civilizations that exist in isolation, not because they are unique or unlucky, but because the physics of their universe does not allow the kind of interconnection that the word galaxy might suggest. The Milky Way contains something between 200 billion and 400 billion stars. If a meaningful fraction of them host technological civilizations, each one exists in a pocket defined by the reachability horizon at their technological level. Those pockets do not overlap at current or near-future capabilities. The civilizations are neighbors in the purely geometrical sense, separated by 4 to 5 light-years on average, but not neighbors in any functional sense. They share the same galaxy and cannot meet in any time frame that matches the duration of their existence as civilizations. There is a version of this that produces a different framing of the Fermi paradox than the one usually discussed. The standard question is, why the galaxy appears uninhabited if intelligence is common? One answer is that intelligence is rare. Another is that civilizations destroy themselves. A third, which sits at the intersection of physics and organizational capacity, is that civilizations are common but permanently isolated, not by choice, not by catastrophe, but by the simple arithmetic of interstellar distance combined with the practical limits of what any civilization can sustain over the relevant timescales. The universe may not be empty. It may be full of isolated pockets, each containing intelligence that broadcasts light and radio waves into the surrounding space, each hearing the light and radio waves of others, and none of them ever meeting, because the meeting requires crossing distances that the physics and the institutional capacity conspire to make permanent barriers. The disturbing element of this framing is not the isolation itself. Isolation is survivable. Civilizations persist without interstellar contact, as we have demonstrated. The disturbing element is the permanence. The barriers are not temporary, not waiting for better technology in the way that many technological barriers eventually fall. They are built into the rate at which stars form, the density at which they distribute across the galactic disk, the speed at which light and matter move, and the timescales over which civilizations maintain coherent purpose. None of these parameters is adjustable by any technology we can conceptually reach from here. Alpha Centauri is the nearest example of this structure. At 4.24 light-years, it is the best case available to us, the minimum version of the interstellar distance problem. And as we have traced across this series of acts, even the minimum version contains within it the full structure of the permanent barrier. The travel time problem, the deceleration problem, the communication delay, the detection limits, the epistemological ceiling, all of it at the closest possible range. What that says about every other case, the ones farther away, the ones even further still, the typical interstellar gap of 4 to 5 light-years repeated 200 billion times across this galaxy alone, is that the structure we have examined here is not exceptional. It is the rule. Alpha Centauri is not difficult because we happen to have bad luck with our nearest neighbor. It is difficult because this is what the nearest neighbor looks like, everywhere, for every civilization in the galaxy. There is still one way to read this that does not end in defeat, and it begins with reframing what the word isolation means in a universe built this way. The space between Earth and Alpha Centauri is not empty. This is not a poetic statement. The interstellar medium between the two systems contains hydrogen and helium gas at a density of roughly 1 atom per cubic centimeter, along with trace quantities of heavier elements, microscopic dust grains, and magnetic fields threading through the region. It is thin by any terrestrial standard, far thinner than the best laboratory vacuum achievable on Earth, but it is not nothing. The corridor between us has contents. Through that corridor, right now, light is moving in both directions. Photons from Alpha Centauri have been arriving at Earth continuously for as long as the Earth has existed, and before that at the cloud of gas and dust that would eventually become Earth. Photons from Earth's sun have been crossing toward Alpha Centauri for the same duration. In the last 130 years, photons carrying the first human radio transmissions have been added to the outbound stream. In the last several decades, light carrying the specific spectral signatures of Earth's cities, its agricultural chemistry, its industrial emissions, has been joining the ordinary solar radiation traveling outward. Alpha Centauri has been receiving all of this, without knowing it, as a component of the general background of electromagnetic radiation in the local stellar neighborhood. The connection is already there. Not the connection we want, not a physical bridge, not a traversed distance, not a presence, but an unbroken, continuous flow of information between the two systems, operating in both directions, at the speed of light, without obstruction. The interstellar medium scatters some of this light and absorbs very little at optical wavelengths across 4 light-years. The photons arrive. They carry whatever information they carry, which is a great deal about the emitting stars, and, at much lower amplitude, about the planets and biospheres associated with them. The exchange has been ongoing for billions of years at the level of starlight, and for about a century at the level of electromagnetic signals carrying the traces of technological activity. What the distance actually prevents, stated precisely, is not connection. It is physical presence at any speed that makes the journey meaningful within the timescales of a civilization or a biological life. Light crosses it without effort. Radio waves cross it without effort. The information channel is open, continuously, in both directions. What cannot cross it, at any speed that makes the transit viable for physical matter, is matter. Not because the corridor is locked, but because the corridor is very long and we are very slow relative to its length. This reframes what the disturbing quality of Alpha Centauri's distance actually is. It is not that the universe has placed a barrier between us and our nearest neighbor. There is no barrier. Light passes through unimpeded. The disturbing quality is that we are a kind of thing, a biological species made of matter operating on biological timescales, for which the physical crossing of that corridor is categorically impractical, while the universe offers no waiver for our category. The distance does not close for life. It does not shorten because we want it to. It is what it is, made of time and light, and we are in it. The word isolation may be the wrong frame. Isolation implies a barrier between things that would otherwise connect. But the photons from Alpha Centauri are arriving at Earth right now, carrying information about the state of those stars as they were 4 years ago, without any effort on our part and without any permission being required. We are not isolated from Alpha Centauri in the way that a room is isolated from another room by a closed door. We are connected to it in the way that a person is connected to a radio station they cannot visit. Continuously receiving, unable to go there, able to transmit back and wait for a delayed response, but not cut off from the information the station emits. What changes when you hold the distance this way is not what is possible. The same limitations apply. The travel time is still 78,000 years at New Horizons speed. The communication delay is still 4.24 years one way. The biosignature detection problem is still as difficult. None of the physics changes with the framing, but the emotional register of the situation shifts in a way that is, I think, more accurate than the register of impenetrable barrier. The distance is not a refusal. It is a feature of the universe that precedes us by billions of years and does not have us in mind. What it means to know this, to understand that we live in a universe where the nearest stellar neighbor is continuously sending us information, where we can read that information with increasing precision, where we can even send information back knowing it will arrive, but where we cannot ourselves go, and cannot confirm current states, and cannot achieve the kind of presence that physical exploration implies. What it means to know all of that is not despair. It is something more like precision. A clear view of the terrain. The photons from Alpha Centauri that have arrived at Earth today will scatter through the atmosphere, reflect off surfaces, be absorbed by the oceans, register in whatever instruments happen to be pointed in the right direction. A small fraction of them will reach the ground. A smaller fraction of those will reach any given surface at any given moment. An even smaller fraction will reach the surface of a human body, its skin absorbing light across a range of wavelengths, converting photons into heat and chemical signals, just as it has always done with the ambient electromagnetic environment of the planet. If you are outside at any point tonight, you will be doing what Earth has always done with Alpha Centauri's light. Receiving it, not reaching it, not visiting it, not communicating with it, receiving it. The photons left those stars 4 years ago and have been crossing 40 trillion kilometers of interstellar space to arrive at this atmosphere, at this surface, at this moment. They will not be the last. More are coming, continuously, and will continue to come as long as those stars burn. The distance is very large. It is what separates here from there. But the light does not respect it as a barrier. It crosses it in both directions, freely, on its own schedule, carrying what it can carry. And what it can carry, it turns out, is quite a lot. The rest, the physical presence, the real-time state, the meeting, those remain on the far side of what the universe permits. What you have right now, in this room, in this moment, is the same as what has always been available, the light. And the light has been traveling a very long time to get here. You are warm right now. Your body is maintaining a temperature of approximately 37 degrees Celsius, which requires a continuous supply of chemical energy, which comes from the breakdown of glucose and other molecules in your cells, which releases heat as a byproduct of the same thermodynamic process that releases energy in any chemical reaction where the products are more stable than the reactants. The warmth you feel in your own skin is the surface expression of billions of simultaneous chemical reactions, each one releasing a small amount of energy as heat, the aggregate of which keeps your internal temperature within the narrow range where the proteins that run your biology maintain their structure and function. It is not a gentle process. It is constant, involuntary, ongoing in every cell of your body, and it will continue as long as you live without requiring any attention from you. The atoms those reactions are occurring in were not always here. The carbon in your cells, the oxygen in the air moving through your lungs right now, the iron carrying oxygen through your blood, the nitrogen in the proteins that make up most of your body's dry mass, none of these elements were present at the formation of the universe. The universe began with hydrogen, helium, and trace amounts of lithium. Everything heavier was made later, inside stars, in the nuclear fusion reactions that power stellar interiors and the explosive processes that scatter stellar material when massive stars die. Every carbon atom in your body was synthesized inside a star that lived and died before our sun formed. Every oxygen atom you are breathing right now was made the same way. You are, in the literal sense of the word, made of stellar ash, the dispersed remnants of nuclear processes that happened in stars that no longer exist billions of years before the Earth formed from the debris field of the solar nebula. The same physics that makes Alpha Centauri inaccessible is the physics that created you. The nuclear reactions operating in the core of Alpha Centauri A right now are identical in type to the reactions that occurred in the stars that built the atoms in your cells. Hydrogen fusing to helium, releasing energy at rates governed by quantum tunneling probabilities and the density and temperature of stellar interiors. The difference between you and a star is not the physics. It is the scale and the organization. At stellar scales and temperatures, the reactions release energy as radiation and heat the surrounding plasma. At the scale of a mitochondrion, at body temperature, the reactions release energy in controlled packets that cells can capture and use. The same universe, the same physics, operating across an enormous range of scales and producing both the star 4 light-years away and the warmth in your hand. You are also, right now, inside a magnetic field. Earth's magnetic field, generated by the motion of molten iron in the outer core, extends tens of thousands of kilometers into space and deflects most of the charged particles in the solar wind before they can reach the upper atmosphere. Without it, the solar wind would interact directly with the atmosphere, gradually stripping it away over geological time. This is, as far as we can determine, what happened at Mars, which lost its global magnetic field billions of years ago and has since lost most of its atmosphere. It may be what is happening at Proxima b right now, under the assault of Proxima's frequent superflares. The air you are breathing exists because this planet has a magnetic field and a stable star and an orbit at a distance that keeps water liquid. Not because the universe arranged these conditions for you, because these conditions exist, and you are here as a consequence of them rather than in spite of them. Life on Earth did not overcome the environment to exist. It arose from within the environment because the environment permitted it, over billions of years of chemistry and biology unfolding within a very specific set of physical boundary conditions. The contrast with what we have spent this night examining is precise. Proxima b orbits in its star's habitable zone at the right distance for liquid water, but faces superflares that may have stripped its atmosphere, and may be tidally locked so that one side bakes and the other freezes. Alpha Centauri A and B may have habitable zone planets, but we cannot confirm it, and their binary gravitational interaction may have disrupted the planet formation process that would have built them. The systems next door are plausible but unconfirmed, possibly hostile to the chemistry of life, possibly empty of everything but geology. Here, inside this building, in this room, the chemistry works. The light from Alpha Centauri is falling on the exterior of this building right now. It has been falling on the surface of the Earth continuously for billions of years, as one small component of the general radiation environment of this region of the galaxy. Inside the building, you are not receiving those photons directly, as walls are opaque at optical wavelengths, but the Earth around you is, and the photons landing on exposed surfaces are doing what photons do when they encounter matter, being absorbed, converted to heat, scattered, or reflected, depending on the material. The light makes no distinction between our nearest stellar neighbor and any other star. It arrives and is received. You have been holding a lot tonight. 4.24 light-years of distance, examined from the inside. The measurement, the structure, the ghost planet, the telescope that cannot look, the binary mechanics, the violence of Proxima, the epistemic limits, the travel time, the communication delay, the biological filters, the structural loneliness. All of it is true. None of it is different from what it was before you listened. And you are still here, in a body that is warm because of stellar reactions in your cells, breathing air that exists because of a magnetic field generated deep in this planet's core, orbiting a stable star at a distance that keeps the water liquid. The universe that contains Alpha Centauri also contains this. The same laws, the same physics, the same history, running at different scales, in different configurations, producing both the inaccessible and the immediate. You have traveled a long way tonight, in the only direction that costs nothing, attention. 4 light-years out, and 19 acts back, you are exactly where you were when you started, which is exactly where the physics placed you, which is, all things considered, a very specific and unlikely place to be. Let the breath slow. Let the body do what it does without your help. The cells will keep running their reactions. The magnetosphere will keep deflecting the solar wind. The light from Alpha Centauri will keep arriving, whether you are awake to receive it or not. You do not have to hold any of this right now. The universe will continue its inventory without you. The distance to Alpha Centauri will remain 4.24 light-years, and it will remain what it has always been. The honest answer to the question of how far away the nearest thing is. Far enough to disturb, close enough to see. Sleep well. The light will still be there in the morning.